Tonight, we begin with a question that has haunted humanity since we first gazed up at the stars. Are we alone in this vast cosmic ocean, or is life thriving on distant worlds we can barely imagine? It's a question that keeps astronomers awake at night, drives billion-dollar space missions, and fundamentally challenges everything we think we know about our place in the universe. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And let me know in the comments where you're tuning in from and what you think the answer might be. It's always fascinating to see who's joining us from around the world. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. In a universe containing an estimated 2 trillion galaxies, each harboring hundreds of billions of stars, the mathematical probability that Earth is the only planet hosting life seems almost absurd. Yet here we are, seemingly alone, listening to the cosmic silence with increasingly sophisticated instruments, wondering if anyone is listening back. The search for extraterrestrial life has evolved from science fiction fantasy to rigorous scientific endeavor. We're no longer asking if other worlds exist. We know they do. Over 6,000 confirmed exoplanets now populate our databases, with thousands more candidates awaiting verification. That's a staggering leap from just 30 years ago, when we knew of exactly 0 worlds beyond our solar system. The floodgates opened, and discoveries poured in faster than we could catalogue them. But discovering planets is just the beginning. The real question is whether any of these distant worlds harbour the chemical signatures of life, the atmospheric fingerprints that would announce to the universe that biology has taken hold. And that search has led us to some of the most exciting and controversial discoveries in modern astronomy. Let's start with the numbers because they're genuinely mind-bending. Our galaxy alone contains an estimated 400 billion stars. If even 1% of those stars host planets, and even 1% of those planets exist in the habitable zone where liquid water can exist, and even 1% of those develop life, we're still talking about 4 million worlds teeming with biology. The Drake equation, formulated in 1961 by astronomer Frank Drake, attempts to quantify these probabilities, though it's more philosophical framework than precise calculation. The equation considers factors like the rate of star formation, the fraction of stars with planets, the number of planets that could support life, and the likelihood that life actually emerges. But here's where it gets interesting. Recent modifications to the Drake equation have incorporated earth science factors that dramatically change the calculations. Researchers now argue that plate tectonics and the presence of both oceans and continents are critical for complex life. When you factor in these geological requirements, the predicted number of communicative civilizations drops by several orders of magnitude. This brings us face to face with what's known as the Fermi paradox. Named after physicist Enrico Fermi, who famously asked, "Where is everybody?" during a lunch conversation in 1950, the paradox highlights a troubling contradiction. If the universe should be teeming with intelligent life, why haven't we encountered any evidence of it? Why aren't our skies filled with alien spacecraft? Why haven't we detected their radio signals or seen evidence of their mega-engineering projects? The silence is deafening, and it's forced scientists to consider some uncomfortable possibilities. Perhaps we're asking the wrong questions. Perhaps we're looking in the wrong places. Or perhaps something prevents most civilizations from reaching the point where they become detectable across interstellar distances. Enter the concept of the Great Filter. This theoretical barrier suggests there's an extremely difficult or improbable step somewhere along the evolutionary path from simple molecules to spacefaring civilizations. The filter could lie behind us, meaning the emergence of complex life or intelligence is extraordinarily rare. In that case, we might be among the few who made it this far. which would be somewhat optimistic for our future prospects. But if the great filter lies ahead of us, the implications are far more sobering. Nuclear warfare, artificial intelligence run amok, climate catastrophe, or biotechnological disasters could represent civilization-ending hurdles that most species fail to overcome. Recent research has even suggested that artificial intelligence itself might be the great filter, with civilizations developing super-intelligent AI systems that ultimately lead to their extinction within a few hundred years of achieving technological sophistication. This possibility becomes especially relevant when we consider that any civilization capable of interstellar communication would likely have already developed advanced AI. If AI consistently leads to civilizational collapse, it would explain both the apparent abundance of potentially habitable worlds and the conspicuous absence of detectable alien intelligence. While we grapple with these existential questions, the search for life continues with unprecedented precision and sophistication. The discovery of exoplanets has accelerated dramatically thanks to space-based telescopes like Kepler and the Transiting Exoplanets Survey satellite. These instruments detect the tiny dimming of starlight when a planet passes in front of its host star, allowing us to determine not just the planet's size and orbit, but potentially the composition of its atmosphere. Red dwarf stars have emerged as particularly promising targets in this search. These small, cool stars make up about 75% of all stars in our galaxy and can remain stable for trillions of years, far longer than our Sun will survive. Planets orbiting red dwarfs can huddle much closer to their stars while remaining in the habitable zone, making them easier to detect and study. Recent breakthroughs have brought us tantalizingly close to detecting potentially habitable worlds in our cosmic neighborhood. The Near-Infrared Planet Searcher has achieved remarkable precision in detecting small, rocky planets around nearby red dwarf stars. For the first time, astronomers have reached the sensitivity needed to detect the gravitational pull of Earth-sized planets around these common stellar neighbors. The discovery of Proxima Centauri d represents a milestone in this effort. Located in the closest star system to our own, just 4.2 light-years away, this planet offers a potential target for detailed study with next-generation telescopes. The fact that we continue finding new worlds in our immediate galactic neighborhood suggests that planetary systems are even more common than our most optimistic estimates predicted. Barnard's star, another nearby red dwarf, has revealed its own planetary system. Astronomers have confirmed at least one world orbiting this star, with hints of 3 additional planet candidates. These discoveries paint a picture of a galaxy where planets are the norm rather than the exception, where virtually every star system hosts worlds of various sizes and compositions. But finding planets is only half the battle. The real breakthrough comes from studying their atmospheres, searching for the chemical signatures that might indicate biological activity. This is where the James Webb Space Telescope has revolutionized our approach to astrobiology. Webb's infrared vision allows it to peer through the atmospheres of distant worlds, analyzing the light filtered through their air to determine chemical composition. This technique, called transmission spectroscopy, can detect water vapor, methane, carbon dioxide, and potentially even more exotic molecules that might indicate biological processes. The most controversial detection has come from the atmosphere of K2-18b, a sub-Neptune exoplanet located 124 light-years from Earth. Initial observations suggested the presence of dimethyl sulfide, a molecule that on Earth is produced exclusively by living organisms, primarily marine microbes. If confirmed, this would represent the strongest evidence yet for biological activity on a world beyond our solar system. However, the scientific community has approached these findings with appropriate skepticism. A NASA-led reanalysis incorporating multiple independent studies found no conclusive evidence of dimethyl sulfide, despite the initially promising detection. The signal remains present in the data, but falls below the rigorous statistical threshold required for definitive confirmation. This ongoing scientific debate highlights the challenges inherent in detecting biosignatures across vast interstellar distances. Even with Webb's unprecedented capabilities, distinguishing between biological and non-biological sources of atmospheric chemicals requires extraordinary precision and multiple independent confirmations. The complexity extends beyond simple detection to understanding the environmental context in which potential biosignatures might exist. Life on Earth produces a distinctive atmospheric disequilibrium, maintaining chemical combinations that wouldn't naturally persist without constant biological input. The presence of oxygen and methane together, for example, represents a powerful biosignature because these gases react with each other and disappear unless continuously replenished. Researchers are now developing more sophisticated approaches that look for these chemical disequilibria rather than individual molecules. By examining the overall energy balance of planetary atmospheres, scientists hope to identify the thermodynamic signatures of biological activity, even if the specific chemistry differs from what we see on Earth. The search extends beyond atmospheric analysis to encompass the broader field of astrobiology, which considers the full range of environments where life might emerge and thrive. Subsurface oceans on moons like Europa and Enceladus represent some of the most promising targets in our own solar system, while recent discoveries of extremophile organisms on Earth continue to expand our understanding of life's resilience and adaptability. These Earth-based discoveries have profound implications for astrobiology. Life thrives in environments previously thought impossible, from the crushing depths of ocean trenches to the highly acidic hot springs of Yellowstone, from the freezing deserts of Antarctica to the radiation-bombarded zones around nuclear reactors. Each new extremophile discovery expands the potential habitable zone around other stars and increases the number of worlds that might support biological activity. The technological revolution in astrobiology shows no signs of slowing. Upcoming missions will carry even more sophisticated instruments capable of detecting increasingly subtle biosignatures. The recently proposed HabEx and LUVOIR space telescopes would dramatically exceed Webb's capabilities, potentially imaging Earth-sized planets directly and analyzing their atmospheres in unprecedented detail. Ground-based astronomy is also pushing new frontiers. The extremely large telescope, currently under construction, will have a mirror 39 meters across, providing resolution sharp enough to potentially detect city lights on nearby exoplanets. Such observations would represent unambiguous technosignatures, evidence of technological civilization rather than simple biological activity. As we stand on the threshold of potentially answering one of humanity's most profound questions, the stakes couldn't be higher. The discovery of life beyond Earth would fundamentally transform our understanding of biology, evolution, and our place in the cosmic order. But equally important is what we might learn if the search continues to yield silence. The search for extraterrestrial intelligence has evolved far beyond the popular image of scientists huddled around radio telescopes, listening for alien broadcasts. Modern SETI represents a sophisticated, multifaceted approach that encompasses everything from artificial intelligence analysis to the search for megastructures that advanced civilizations might construct around their stars. The Breakthrough Listen initiative stands as the most comprehensive and well-funded SETI program ever undertaken. With a $100 million budget spread across 10 years, this project observes for thousands of hours annually using some of the world's most powerful radio telescopes. The Green Bank Observatory in West Virginia and the Parkes Observatory in Australia scan the skies continuously, analyzing data streams that would have overwhelmed previous generations of computers. The sensitivity achieved by these modern searches is genuinely staggering. When researchers recently observed the interstellar object designated 3I Atlas, using the Green Bank telescope, they reach sensitivity levels capable of detecting transmissions as weak as a mobile phone at interstellar distances. Think about that for a moment. If an alien civilization were using technology comparable to our own cell phones, we could potentially detect those signals from dozens of light years away. Yet the searches continue to yield silence. No artificial signals, no obvious technosignatures, no evidence of the radio chatter that should accompany any technological civilization similar to our own. This absence has forced researchers to reconsider their fundamental assumptions about how alien intelligence might manifest itself. Recent innovations in SETI methodology focus on detecting spillover from routine interplanetary communications rather than intentional beacon signals. This approach recognizes that any spacefaring civilization would need to maintain contact with spacecraft, satellites, and colonies throughout their solar system. These communications would necessarily be directed and powerful, potentially detectable by our instruments, even if not intended for interstellar reception. The mathematics become compelling when you consider orbital mechanics. Planetary alignments create predictable windows when such communications would be aimed in our direction. Researchers estimate a 77% chance of detecting signals from a civilization with technology comparable to our own during optimal alignment periods, assuming they exist within approximately 23 light-years of Earth. Artificial intelligence has begun revolutionizing SETI research in ways that would have seemed impossible just a few years ago. Machine learning algorithms now process data streams at rates exceeding 86 gigabits per second, identifying patterns that human analysts might overlook entirely. These systems don't just accelerate the discovery of known signal types. They can recognize completely novel signal morphologies that we haven't even imagined. Advanced civilizations might use burst-like transmissions, frequency-modulated signals, or communication protocols based on physical principles we haven't yet discovered. AI systems, trained on vast datasets of natural astronomical phenomena, can potentially distinguish artificial signals from the cosmic background, even if those signals follow patterns unlike anything in our technological experience. The integration of high-energy astronomy into SETI research represents another frontier expansion. X-ray and gamma-ray emissions from technological processes might be detectable across much greater distances than radio signals. A civilization harnessing the energy of their entire star, for example, would produce distinctive high-energy signatures visible from thousands of light-years away. These Kardashev Type II civilizations, named after Soviet astronomer Nikolai Kardashev, would construct massive engineering projects like Dyson spheres or swarms of solar collectors around their stars. Such megastructures would create observable dimming patterns unlike anything produced by natural astronomical phenomena. Several candidate objects have been identified, including the famous star designated KIC 8462852, though natural explanations remain more likely for all current observations. The philosophical implications of SETI extend far beyond the technical challenges of detection. The continued absence of obvious alien signals forces us to confront uncomfortable questions about the nature of intelligence and technological development. Perhaps civilizations consistently destroy themselves shortly after achieving radio capability. Perhaps they develop communication technologies so advanced that their signals appear indistinguishable from natural phenomena to our primitive instruments. Or perhaps intelligence itself follows patterns we don't recognize. Our search strategies assume that alien civilizations would develop radio technology, construct megastructures, or engage in activities detectable by electromagnetic emissions. But intelligence might evolve along completely different trajectories, producing technological signatures that remain invisible to our current detection methods. The concept of convergent evolution suggests that similar environmental pressures produce similar biological solutions across different lineages. Eyes evolved independently dozens of times on Earth. Flight emerged separately in insects, birds, bats, and pterosaurs. But intelligence appears to be far rarer, having evolved to technological levels only once in Earth's 4 billion-year biological history. This rarity might reflect genuine constraints on the development of complex cognition. Intelligence requires enormous metabolic investment. Human brains consume approximately 20% of our total energy budget, a massive overhead that must provide sufficient survival advantage to justify the cost. Perhaps most environmental niches favor other survival strategies over the development of abstract reasoning and technological manipulation. The social requirements for technological civilization add another layer of complexity. Human technological development required not just individual intelligence, but sophisticated cooperation, communication systems, and the ability to accumulate knowledge across generations. These social innovations might be even rarer than individual intelligence, creating additional filters that prevent most intelligent species from achieving technological capabilities. Recent research into the role of catastrophic events in technological development suggests that civilizations might face predictable crises that determine their long-term survival prospects. Climate change, resource depletion, nuclear warfare, artificial intelligence risks, and biotechnological disasters represent potential extinction filters that most civilizations might fail to navigate successfully. The timing of these crises relative to technological development could be crucial. A civilization that develops nuclear weapons before achieving sustainable energy, or artificial intelligence before establishing robust safety protocols, might face existential risks that prove insurmountable. The window between achieving dangerous technologies and developing the wisdom to use them safely might be vanishingly narrow. This possibility becomes especially relevant when considering the pace of technological acceleration. Human civilization has compressed most of its technological development into the last few centuries, with the most rapid changes occurring within living memory. If similar acceleration characterizes technological development generally, then civilizations might face existential decision points within decades or centuries of achieving radio capability. The implications for SETI are sobering. If technological civilizations typically survive for only a few hundred years after achieving detectability, then the number of contemporaneous civilizations in our galaxy could be orders of magnitude smaller than optimistic estimates suggest. We might be searching for signals from civilizations that existed millions of years ago, or won't emerge for millions of years in the future. The temporal aspect of the search adds another dimension of difficulty to an already challenging problem. Even if the galaxy has hosted thousands or millions of technological civilizations throughout its history, the probability that any two would exist simultaneously becomes vanishingly small given the vast timescales involved. Yet the search continues with growing sophistication and expanding scope. New theoretical frameworks consider the full spectrum of possible technosignatures, from atmospheric pollution on exoplanets to the waste heat signatures of advanced energy utilization. Researchers examine everything from unusual isotope ratios that might indicate nuclear technology to the geometric patterns of asteroid mining operations that could reveal industrial activity in distant solar systems. The next generation of telescopes promises to revolutionize our detection capabilities once again. The extremely large telescope will provide resolution sharp enough to potentially observe individual continents on nearby exoplanets. Space-based interferometers could achieve even greater precision, mapping the surfaces of distant worlds in unprecedented detail. These instruments might detect the infrared signatures of cities, the geometric patterns of agriculture, or the atmospheric pollution that accompanies industrial development. Such observations would provide unambiguous evidence of technological activity, finally answering the question that has driven decades of searching. But perhaps the most profound realization emerging from modern astrobiology and SETI research is how little we actually understand about the nature and prevalence of life and intelligence in the universe. Every new discovery, from extremophile organisms to exoplanet atmospheres, reveals additional complexity and possibility that our theories struggle to accommodate. The universe might be teeming with life forms so alien that we lack the conceptual framework to recognize them. Intelligence might manifest in ways that bear no resemblance to our technological civilization. Or we might indeed be alone, the sole example of matter organizing itself into conscious, questioning beings capable of pondering its own existence. As we push deeper into this cosmic mystery, armed with increasingly powerful instruments and sophisticated theoretical frameworks, we're discovering that the question of our cosmic loneliness leads to equally profound questions about the nature of consciousness, the meaning of intelligence, and the ultimate fate of complex systems in an evolving universe. The search continues, driven by our fundamental need to understand our place in the cosmic story, whether that story unfolds in solitude or in the company of countless other conscious beings scattered among the stars. The question of whether we're truly alone becomes even more complex when we consider the sheer diversity of environments where life might emerge and thrive. Our understanding of habitability has undergone a radical transformation in recent decades, expanding far beyond the traditional concept of a narrow zone around sun-like stars where liquid water can exist on planetary surfaces. Consider the subsurface oceans that likely exist beneath the icy shells of Jupiter's moon Europa and Saturn's moon Enceladus. These hidden seas contain more water than all of Earth's oceans combined, warmed by tidal heating from their massive parent planets. Recent observations have detected water vapor plumes erupting from Enceladus's surface, carrying complex organic molecules that hint at hydrothermal activity on the seafloor below. These discoveries force us to reconsider what constitutes a habitable world. The traditional habitable zone, sometimes called the Goldilocks zone, assumes that planets need to orbit at just the right distance from their stars to maintain liquid water on their surfaces. But subsurface oceans can exist far beyond these narrow bands, protected from the vacuum of space by kilometers of ice and rock. The implications are staggering. If moons with subsurface oceans represent viable habitats for life, then the number of potentially habitable worlds in our galaxy increases by orders of magnitude. Every gas giant could host multiple moon systems, each potentially harboring its own biosphere in the dark depths beneath frozen surfaces. This realization has fundamentally altered our approach to astrobiology. Rather than focusing exclusively on Earth-like planets orbiting Sun-like stars, researchers now consider a vast array of alternative scenarios. Tidally locked planets around red dwarf stars, where one hemisphere experiences eternal day, while the other remains forever frozen in darkness, might maintain stable atmospheric circulation that creates temperate zones between the extremes. Super-Earths, planets significantly more massive than our own world but smaller than Neptune, represent another category of potentially habitable worlds. These planets might maintain thick atmospheres and active geology for billions of years longer than Earth-sized worlds, providing stable environments for the evolution of complex life. The study of extremophile organisms on our own planet continues to expand the boundaries of where life might exist. Deep in the Earth's crust, microorganisms thrive in conditions that would instantly kill most surface life. These subsurface communities derive energy from chemical reactions involving rock and water, completely independent of sunlight or surface conditions. Some of these organisms live at temperatures exceeding the boiling point of water, sustained by pressures that keep water liquid at temperatures that would vaporize it at the surface. Others survive in highly acidic or alkaline conditions, or in environments bombarded by radiation levels that would prove lethal to most known life forms. Each new discovery of extremophile life expands the potential habitable envelope around other stars and increases the number of worlds that might support biological activity. If life can thrive in Earth's most hostile environments, then planets we might dismiss as uninhabitable could actually host thriving ecosystems adapted to conditions we consider impossible. The chemical signatures of life present another layer of complexity in our search for extraterrestrial biology. On Earth, living organisms have fundamentally altered the composition of our planet's atmosphere, creating chemical combinations that would not exist without constant biological input. The simultaneous presence of oxygen and methane in our atmosphere, for example, represents a powerful biosignature, because these gases react with each other and would disappear within geological timescales without continuous replenishment. But alien life might produce completely different atmospheric signatures. Organisms adapted to different stellar environments, atmospheric compositions, or evolutionary pressures might create biosignatures unlike anything we see on Earth. The challenge becomes distinguishing between biological and non-biological sources of unusual atmospheric chemistry across interstellar distances. Recent theoretical work has focused on identifying universal principles of life that might apply regardless of specific biochemistry or environmental conditions. All living systems must extract energy from their environment, maintain organization against entropy, reproduce with variation, and evolve through natural selection. These fundamental requirements might produce detectable signatures even if the specific chemistry differs radically from terrestrial biology. The concept of agnostic biosignatures represents an attempt to identify life without making assumptions about its specific biochemistry. Rather than searching for particular molecules like oxygen or phosphine, this approach looks for patterns in atmospheric chemistry that indicate disequilibrium maintained by energy input, the thermodynamic signature of living systems. Artificial intelligence and machine learning are beginning to revolutionize this search by identifying subtle patterns in spectroscopic data that human analysts might overlook. These algorithms can detect correlations between multiple atmospheric components that might indicate biological processes, even when individual molecules don't obviously suggest biological activity. The James Webb Space Telescope has provided our first glimpse of what this new era of atmospheric analysis might reveal. Its observations of the TRAPPIST-1 system, which hosts 7 Earth-sized planets orbiting an ultra-cool red dwarf star, will test our ability to detect biosignatures around the most common type of star in our galaxy. Initial observations have already revealed the complex atmospheric dynamics of these worlds. TRAPPIST 1b, the innermost planet, appears to lack a substantial atmosphere, likely stripped away by intense stellar radiation. But the outer planets in the system might maintain thick atmospheres capable of supporting liquid water and potentially biological activity. The precision required for these measurements pushes the limits of current technology. Detecting biosignatures requires distinguishing the tiny spectral features produced by trace gases from the overwhelming signal of the host star and the planet's own thermal emission. The signal-to-noise ratios involved are so challenging that multiple observations and sophisticated statistical analysis are required to reach definitive conclusions. This technical complexity explains why the initial detection of potential biosignatures in K2-18b's atmosphere remains controversial. The dimethyl sulfide signal, while present in the data, falls below the rigorous statistical threshold required for scientific confirmation. Multiple independent research groups continue analyzing the same observations, sometimes reaching different conclusions about the significance of the detected features. The controversy highlights a fundamental challenge in the search for extraterrestrial life. The stakes are so high and the implications so profound that the scientific community demands extraordinary evidence before accepting claims of biological activity on distant worlds. False positives could mislead our understanding of life's prevalence in the universe. while false negatives might cause us to overlook genuine biosignatures. This careful approach reflects lessons learned from previous claims of extraterrestrial life that failed to withstand scrutiny. The supposed microfossils in the Martian meteorite, ALH 84001. The controversial detection of phosphine in Venus's atmosphere and other high-profile claims have taught researchers to approach potential biosignatures with appropriate skepticism and rigorous verification procedures. The search for life extends beyond atmospheric analysis to encompass the broader context of planetary evolution and habitability. Understanding how planets form, evolve, and maintain conditions suitable for life requires integrating knowledge from astronomy, geology, chemistry, and biology into a comprehensive framework for assessing habitability. Recent research has revealed the critical role of planetary magnetic fields in maintaining habitable conditions. Earth's magnetic field deflects charged particles from the solar wind that would otherwise strip away our atmosphere over geological timescales. Mars likely lost much of its atmosphere after its magnetic field weakened, transforming a potentially habitable world into the cold, dry planet we observe today. The presence or absence of magnetic fields around exoplanets could therefore serve as a crucial factor in assessing their long-term habitability. Detecting these magnetic fields across interstellar distances represents another technical challenge for future space-based observatories, but one that could provide important clues about planetary habitability. Plate tectonics represents another factor increasingly recognized as crucial for maintaining habitable conditions over geological timescales. Earth's shifting crustal plates drive a carbon cycle that regulates atmospheric composition and global temperature, preventing our planet from experiencing the runaway greenhouse effect that transformed Venus into an infernal world. Planets without active plate tectonics might struggle to maintain stable climates over the billions of years required for complex life to evolve. This requirement could significantly reduce the number of truly habitable worlds, even among planets that appear suitable based on their size, orbital distance, and atmospheric composition. The temporal dimension of habitability adds another layer of complexity to assessing the probability of life on distant worlds. Planets must remain habitable for sufficient time to allow life to emerge, evolve, and potentially develop intelligence. Earth required nearly 4 billion years to produce technological civilization, suggesting that stable long-term habitability might be essential for the emergence of detectable intelligence. Stellar evolution complicates this timeline. Sun-like stars gradually brighten over their lifetimes, slowly pushing the habitable zone outward, and eventually making their planets too hot to support liquid water. Red dwarf stars remain stable for much longer periods, but their frequent flaring might sterilize planetary surfaces or strip away atmospheres. The Goldilocks principle applies not just to orbital distance, but to stellar properties, planetary characteristics, and evolutionary timescales. Finding worlds that satisfy all these requirements simultaneously might prove far more challenging than early estimates suggested, potentially explaining why our searches haven't yet yielded definitive evidence of extraterrestrial life. As we push deeper into this cosmic mystery, each new discovery reveals additional layers of complexity that our theories must accommodate. The universe appears to be neither uniformly hostile to life nor obviously teeming with biological activity. Instead, it presents a nuanced landscape of possibilities where life might emerge under specific conditions, but face numerous challenges to long-term survival and evolution. The continued absence of obvious alien signals or unambiguous biosignatures doesn't necessarily imply that we're alone. It might simply reflect the genuine difficulty of detecting life across vast interstellar distances, the rarity of conditions suitable for complex evolution, or the brief timescales during which technological civilizations remain detectable. Our growing understanding of life's requirements and constraints suggests that while simple life might be relatively common in the universe, complex ecosystems capable of producing detectable biosignatures or technological civilizations might be extraordinarily rare. The emergence of intelligence might represent such an unlikely convergence of favorable conditions that civilizations like our own occur only once per galaxy per billion years. Yet the search continues with ever-increasing sophistication and sensitivity. Each negative result provides valuable information about the nature and prevalence of life in the universe, gradually constraining the parameters that govern biological emergence and evolution. Whether we ultimately discover that we're part of a vast community of cosmic life, or that we represent a singular experiment in consciousness and complexity, the answer will fundamentally transform our understanding of our place in the universe. The question that began our journey tonight, whether we're truly alone or part of a larger cosmic community, remains tantalizingly open. But with each passing year, our tools grow sharper, our understanding deeper, and our ability to peer into the atmospheres of distant worlds more precisely. We stand at a remarkable inflection point in the history of human knowledge, where theoretical frameworks meet cutting-edge observation in ways that would have seemed impossible just decades ago. The tools we're developing to answer these profound questions about cosmic loneliness are advancing at a pace that sometimes feels almost supernatural in its precision and capability. The upcoming generation of ground-based telescopes promises to revolutionize our detection capabilities in ways that border on science fiction. The extremely large telescope, currently under construction in Chile's Atacama Desert, will possess a primary mirror 39 meters across. To put that in perspective, this single mirror will collect 15 times more light than all current large telescopes combined. Its resolution will be sharp enough to potentially observe the geometric patterns of agriculture on nearby exoplanets, or detect the infrared signatures of cities on worlds orbiting the closest stars. But even these groundbreaking capabilities pale in comparison to what space-based interferometry might achieve. By linking multiple space telescopes in coordinated arrays, astronomers could create virtual mirrors hundreds or even thousands of kilometers across. Such instruments could map the surfaces of distant worlds in unprecedented detail, revealing seasonal changes in vegetation, the geometric patterns of potential infrastructure, or the atmospheric pollution signatures that accompany industrial development. The technical challenges involved in these observations push the absolute limits of current engineering. Detecting the thermal emission from a planet orbiting another star requires distinguishing a signal millions of times fainter than the star itself. It's like trying to spot a firefly hovering next to a searchlight from thousands of miles away. Yet advances in coronagraph technology and adaptive optics are making these impossible observations increasingly routine. Recent breakthroughs in quantum sensing and photon detection have reached sensitivities approaching fundamental physical limits. New detector arrays can register individual photons with timing precision measured in femtoseconds, allowing astronomers to extract information from the faintest possible signals. These technologies enable measurements so precise that they can detect the gravitational influence of planets smaller than Earth orbiting stars hundreds of light-years distant. The integration of artificial intelligence into astronomical data analysis represents another quantum leap in capability. Machine learning algorithms trained on vast datasets of stellar spectra can identify patterns invisible to human analysis, potentially recognizing the signatures of technological activity that follow principles we haven't yet discovered. These systems process information at rates that would overwhelm traditional analysis methods, scanning millions of stars simultaneously for any deviation from natural astrophysical phenomena. Consider the implications of automated pattern recognition applied to the search for megastructures. A Kardashev. Type 2 civilization might construct solar collectors, space habitats, or computational matrices around their host star that create distinctive dimming patterns, unlike anything produced by natural astronomical phenomena. Current AI systems can analyze light curves from hundreds of thousands of stars, flagging unusual periodic variations that might indicate artificial structures. The famous star KIC 8462852, popularly known as Tabby's star, demonstrated both the promise and the challenges of this approach. Its irregular dimming pattern, sometimes blocking more than 20% of the star's light, initially defied conventional explanation. While subsequent observations favor natural causes involving circumstellar dust, the episode highlighted how automated surveys might identify genuinely artificial phenomena among the vast catalogue of stellar observations. Recent advances in radio astronomy have achieved sensitivity levels that would detect technology comparable to our own across significant interstellar distances. The Square Kilometre Array, currently under construction, will possess collecting area equivalent to a radio dish 1 kilometre in diameter. This enormous instrument will be sensitive enough to detect airport radar systems operating around nearby stars, providing unprecedented capability to identify the electromagnetic signatures of technological civilization. But perhaps the most intriguing development involves the search for what researchers term techno-signatures that might persist long after the civilizations that created them have vanished. Advanced materials, isotopic ratios indicating nuclear technology, or the geometric arrangement of asteroids stripped for resources could remain detectable for millions of years after their creators disappeared. This temporal persistence raises fascinating possibilities about archaeological astronomy. The search for evidence of ancient technological activity preserved in the geological or astronomical record. If civilizations consistently last only a few centuries after achieving radio capability, then the galaxy might be littered with the remnants of thousands of extinct technological species, their presence detectable to sufficiently advanced archaeological techniques. The concept extends to our own solar system, where some researchers have proposed searching for artifacts left by ancient visitors. While no credible evidence for such artifacts has emerged, the systematic survey of near-Earth asteroids and Lagrange points represents a legitimate scientific endeavor with potential implications for understanding whether technological civilizations have previously explored our local region of space. Recent theoretical work has explored how we might recognize signs of geoengineering or terraforming on distant worlds. A civilization attempting to modify planetary atmospheres might produce distinctive chemical signatures detectable through transmission spectroscopy. The sudden appearance of industrial gases in a planet's atmosphere, or unusual isotopic ratios indicating nuclear processes, could provide unambiguous evidence of technological intervention. These searches require extraordinary precision in distinguishing artificial from natural processes. Atmospheric chemistry involves countless variables, and many apparently anomalous observations can be explained through complex but purely natural mechanisms. The scientific standards for confirming technological signatures must be even more rigorous than those applied to potential biosignatures, given the profound implications of such discoveries. The psychological dimensions of the search have become increasingly important as our detection capabilities approach the threshold where definitive answers might finally emerge. Decades of negative results have forced researchers to confront the possibility that technological civilizations might be extraordinarily rare, with implications that extend far beyond academic astronomy. If we are indeed alone, or nearly alone, among the hundreds of billions of stars in our galaxy, then consciousness and intelligence represent far more precious and fragile phenomena than most people realize. The responsibilities that come with being the only known example of matter organizing itself into conscious, questioning beings capable of science and philosophy would be genuinely overwhelming. Conversely, the discovery of even microbial life on another world would fundamentally transform our understanding of biology and our place in the cosmic order. Life emerging independently on two different worlds within a single stellar system would suggest that biological activity is a common, perhaps inevitable outcome of planetary evolution under suitable conditions. The implications cascade through multiple disciplines. If simple life proves common but complex ecosystems rare, it suggests that the emergence of multicellular organisms represents a genuine evolutionary bottleneck. If complex life is widespread but intelligence extremely rare, it implies that consciousness requires such specific conditions that technological civilizations might be separated by millions of years and thousands of light years. Recent research into the role of mass extinction events in shaping evolutionary complexity has revealed how catastrophic episodes might actually accelerate the development of intelligence. Earth's history includes at least 5 major extinction events that dramatically reduced biodiversity, but also created ecological niches that favored adaptability and problem-solving capabilities. The asteroid impact that ended the age of dinosaurs 65 million years ago, for example, eliminated dominant reptilian species, but created opportunities for small, adaptable mammals to diversify and eventually evolve complex cognition. Without this catastrophic intervention, Earth might still be dominated by reptilian species with limited cognitive capabilities. This pattern suggests that the development of intelligence might require not just stable conditions for biological evolution, but also periodic disruptions that favor cognitive adaptability over other survival strategies. The timing and severity of these disruptions could represent another filter that determines whether planets develop technological species. The social and cultural prerequisites for technological development add additional layers of complexity to the emergence of detectable civilizations. Human technological advancement required not just individual intelligence, but sophisticated cooperation, abstract communication systems, and the cultural transmission of knowledge across generations. Archaeological evidence suggests that anatomically modern humans existed for over 100,000 years before developing agriculture, writing systems, and the technological capabilities that define civilization. The transition from hunter-gatherer societies to technological civilization might represent an extremely unlikely cultural phase transition that most intelligent species never successfully navigate. Language appears to be particularly crucial in this transition. The ability to communicate abstract concepts, preserve knowledge across generations, and coordinate complex group activities seems essential for technological development. Yet the emergence of sophisticated language capabilities might itself require specific evolutionary pressures that rarely occur in natural environments. Recent studies of cetacean communication, avian tool use, and primate social learning have revealed remarkable cognitive abilities in non-human species. Yet none have approached the threshold of technological manipulation of their environment. This observation suggests that the gap between general intelligence and technological capability might be far wider than commonly assumed. The temporal coincidence of various technological breakthroughs in human history also raises questions about whether technological development follows predictable patterns or depends on unlikely historical contingencies. The simultaneous development of agriculture in multiple isolated human populations suggests some inevitability to this transition. Yet the subsequent pace of technological advancement has varied dramatically across different cultures and historical periods. If technological development requires specific cultural and environmental conditions that rarely coincide, then the number of detectable civilizations could be orders of magnitude smaller than estimates based purely on biological considerations. The window during which civilizations remain detectable might be vanishingly brief compared to the cosmic timescales involved in stellar and galactic evolution. These considerations have led some researchers to propose that we might be living during a unique epoch in cosmic history when technological civilizations are just beginning to emerge. The universe might be transitioning from a phase dominated by stellar formation and planetary evolution to one where intelligence and consciousness become significant factors in cosmic development. This cosmic perspective suggests that our current searches for extraterrestrial intelligence might be occurring at precisely the moment when such searches become possible, but before widespread technological civilizations have had time to develop and spread throughout the galaxy. We might be among the first generation of conscious beings capable of asking these questions on a cosmic scale. The philosophical implications of this possibility extend far beyond the technical challenges of detection. If consciousness and intelligence represent genuinely rare and recent developments in cosmic evolution, then the emergence of beings capable of contemplating their own existence and questioning their place in the universe might represent one of the most significant events in the history of matter and energy. The responsibility that comes with this realization is genuinely staggering. Every decision we make about the future of human civilization, every choice about how we develop and deploy powerful technologies, every action that affects our planet's habitability carries implications that extend far beyond our immediate concerns. The search for extraterrestrial life and intelligence has evolved from a scientific curiosity to an existential inquiry that touches on the deepest questions about consciousness, meaning, and cosmic purpose. Whether we ultimately discover that we're part of a vast community of intelligent beings, or that we represent a singular experiment in cosmic self-awareness, the answer will fundamentally reshape our understanding of what it means to exist as conscious entities in an evolving universe. As we continue pushing the boundaries of detection and analysis, armed with increasingly sophisticated instruments and theoretical frameworks, we're approaching the threshold where definitive answers to these ancient questions might finally become possible. The next few decades could witness discoveries that transform not just astronomy and biology, but our fundamental conception of our place in the cosmic story that continues unfolding around us. The silence we've encountered so far in our searches might reflect the genuine rarity of consciousness in the universe, or it might simply indicate that we haven't yet developed the sensitivity and sophistication necessary to detect the subtle signatures of life and intelligence scattered among the stars. Either answer would be profound, but for very different reasons. The silence might be telling us something we're not quite ready to hear. Recent developments in astrobiology have begun to challenge our most basic assumptions about what constitutes a habitable environment and how life might manifest itself across the cosmos. The traditional approach of searching for Earth-like conditions around Sun-like stars is giving way to a far more nuanced understanding of the countless ways biology might take hold in the universe. Consider the recent discovery of subsurface chemosynthetic ecosystems in Earth's deepest ocean trenches, where life thrives in complete darkness at crushing pressures and temperatures that would boil water at sea level. These organisms derive energy entirely from chemical reactions involving hydrogen sulfide and methane, creating complex food webs that exist independently of sunlight. The implications are staggering. If similar processes occur on other worlds, then the number of potentially habitable environments expands exponentially. Jupiter's moon Europa has become a focal point for this expanded definition of habitability. Beneath its frozen surface lies an ocean containing twice as much water as all Earth's oceans combined. Recent observations have detected complex organic molecules in the plumes of water vapor that occasionally erupt from cracks in the ice. These plumes carry materials from the ocean depths, providing a window into an alien ecosystem that might have existed for billions of years. The chemistry detected in these plumes suggests hydrothermal activity on Europa's seafloor, similar to the volcanic vents that support Earth's deep sea communities. If life exists in Europa's hidden ocean, it represents a completely independent genesis of biology, proving that life is not a cosmic accident, but a natural consequence of suitable chemical conditions. Saturn's moon, Enceladus, presents an even more compelling case. The Cassini spacecraft detected not just water vapor in its plumes, but complex organic compounds, including formaldehyde, acetylene, and propane. More intriguingly, the ratio of hydrogen to water in these emissions suggests ongoing serpentinization reactions between water and rock, the same process that supports extremophile communities in Earth's oceanic crust. These discoveries have forced astrobiologists to reconsider the very definition of a habitable world. The traditional habitable zone around stars assumes planets need surface liquid water, but subsurface oceans can exist far beyond these narrow bands, protected by kilometers of ice and rock from the harsh radiation environment of space. The mathematics become overwhelming when you consider that every gas giant in our solar system hosts multiple large moons, and similar systems likely exist around billions of other stars throughout the galaxy. If moons with subsurface oceans represent viable habitats, then the number of potentially life-bearing worlds could exceed the number of planets by orders of magnitude. But detecting life in these hidden oceans presents extraordinary technical challenges. The ice shells covering these subsurface seas range from several kilometers to potentially hundreds of kilometers thick. Any biosignatures would need to travel through this barrier and reach the surface before we could detect them from orbit. Future missions to Europa and Enceladus will carry increasingly sophisticated instruments designed to analyze plume materials in real time. The Europa Clipper mission will perform dozens of close flybys, mapping the ice shell thickness and searching for areas where the subsurface ocean might be closest to the surface. Subsequent missions might actually land on these worlds and drill through the ice to reach the oceans below. The technical challenges involved in such missions push the absolute limits of current space exploration capabilities. Drilling through kilometers of ice in the extreme cold and radiation environment around Jupiter requires technologies that don't yet exist. The drill must be completely sterile to avoid contaminating any potential alien ecosystem, yet robust enough to penetrate ice harder than concrete in an environment where temperatures reach -200 degrees Celsius. Recent advances in autonomous drilling systems developed for Antarctic ice sheet exploration are beginning to make such missions feasible. These systems use heated elements and high-pressure jets to melt through ice while maintaining sterile conditions, potentially providing the technology needed to reach subsurface oceans on distant moons. The search for biosignatures has also expanded beyond traditional chemical markers to encompass more subtle indicators of biological activity. Living systems create distinctive patterns in their environment that persist long after individual organisms die. These patterns include isotopic ratios, mineral formations, and even the geometric arrangements of chemical deposits that biological processes tend to produce. On Earth, stromatolites formed by ancient cyanobacteria create layered rock structures that remain recognizable billions of years after the organisms that built them disappeared. Similar formations on other worlds could provide evidence of past or present biological activity, even if no living organisms remain detectable. Recent research has identified dozens of potential biosignature molecules that different types of life might produce. Phosphine, dimethyl sulfide, ammonia, and various organic sulfur compounds could all indicate biological processes under specific environmental conditions. The challenge lies in distinguishing between biological and geological sources of these chemicals across interstellar distances. Venus recently became the center of a major biosignature controversy when researchers claimed to detect phosphine in its atmosphere. On Earth, phosphine is produced almost exclusively by anaerobic bacteria, making it a potentially powerful biosignature. The initial detection suggested concentrations far too high to be explained by known geological processes, leading to speculation about aerial microbes surviving in Venus's upper atmosphere. However, subsequent observations and reanalysis of the original data have failed to confirm the phosphine detection. The controversy highlights both the promise and the pitfalls of remote biosignature detection. Even with sophisticated instruments and careful analysis, distinguishing between biological and non-biological sources of atmospheric chemicals remains extraordinarily challenging. The James Webb Space Telescope has begun to transform our approach to atmospheric analysis on exoplanets. But the precision required for definitive biosignature detection pushes even this remarkable instrument to its limits. Detecting trace gases in the atmospheres of distant worlds requires measurements accurate to parts per billion, comparable to detecting a teaspoon of sugar dissolved in a swimming pool. Recent observations of the TRAPPIST-1 system have demonstrated both the possibilities and the limitations of current atmospheric analysis techniques. This system hosts 7 Earth-sized planets orbiting an ultra-cool red dwarf star, with several worlds potentially located in the habitable zone where liquid water could exist on their surfaces. Initial Webb observations have revealed that the innermost planets lack substantial atmospheres, likely stripped away by intense stellar radiation during their formation. But the outer planets in the system might maintain thick atmospheres capable of supporting liquid water and potentially biological activity. Follow-up observations will search for water vapor, methane, and other molecules that might indicate habitable conditions. The precision required for these measurements has led to the development of new analysis techniques that extract maximum information from limited observational data. Researchers now use sophisticated statistical methods that can identify weak signals buried in noise, potentially detecting biosignatures even when individual observations remain inconclusive. Machine learning algorithms trained on vast data sets of atmospheric chemistry are beginning to identify patterns that human analysts might overlook. These systems can correlate multiple atmospheric components to search for the chemical disequilibria that living systems create, potentially recognizing biosignatures that don't rely on any single molecular species. The concept of agnostic biosignatures represents a fundamental shift in how we approach the search for extraterrestrial life. Rather than searching for specific molecules like oxygen or methane, this approach looks for thermodynamic signatures of energy flow and chemical organization that characterize all living systems regardless of their specific biochemistry. Living organisms maintain themselves in states far from chemical equilibrium, constantly extracting energy from their environment to build and maintain complex molecular structures. This process creates distinctive patterns in atmospheric chemistry that should be detectable even if the specific molecules involved differ completely from those produced by Earth life. Recent theoretical work has identified several universal signatures of living systems that should apply regardless of the specific chemistry involved. These include the maintenance of chemical gradients, the production of complex organic molecules from simple precursors, and the creation of periodic cycles in atmospheric composition that reflect biological rhythms. The search for these universal signatures requires unprecedented precision in measuring atmospheric composition over time. Seasonal variations, daily cycles, and longer-term trends in atmospheric chemistry could all provide evidence of biological activity. But detecting these patterns requires sustained observation campaigns spanning multiple years. The upcoming extremely large telescope will provide the spatial resolution necessary to study individual hemispheres of nearby exoplanets, potentially detecting seasonal changes in atmospheric composition that might indicate biological activity. Such observations could reveal whether potentially habitable worlds show the dynamic atmospheric chemistry characteristic of living systems. But perhaps the most intriguing development in astrobiology involves the growing recognition that intelligence itself might be far more common in the universe than technological civilization. Recent studies of animal cognition have revealed sophisticated problem-solving abilities, complex communication systems, and even cultural transmission of learned behaviors in species ranging from dolphins and elephants to octopuses and crows. These discoveries suggest that intelligence, defined as the ability to solve novel problems and adapt to changing environments, might be a relatively common outcome of evolutionary processes. However, the transition from general intelligence to technological manipulation of the environment appears to be far more rare and might require specific evolutionary pressures that seldom occur in natural settings. Human technological development depended not just on intelligence, but on a remarkable combination of social cooperation, abstract language, fine motor control, and the ability to manipulate fire and tools. The convergence of all these factors might represent such an unlikely coincidence that technological species emerge only once per galaxy per billion years. This possibility has profound implications for the search for extraterrestrial intelligence. If consciousness and problem-solving abilities are relatively common, but technological development extremely rare, then the universe might be filled with intelligent beings who never develop the capability to communicate across interstellar distances. Ocean-dwelling intelligence presents a particularly intriguing case study. Dolphins, whales, and octopuses demonstrate remarkable cognitive abilities, but have no evolutionary pressure to develop technology. An intelligent aquatic species on another world might develop complex societies, sophisticated communication, and even scientific understanding of their environment without ever creating detectable technological signatures. The temporal dimension of intelligence adds another layer of complexity to these considerations. Earth's biosphere has hosted intelligent species for millions of years, but technological civilization emerged only within the last few thousand years. If similar patterns characterize other worlds, then planets might host intelligent life for vast periods without producing detectable technological signatures. Recent research into the cognitive requirements for technological development has identified several key factors that might determine whether intelligent species develop detectable technology. Abstract reasoning, long-term planning, cooperative social structures, and the ability to transmit knowledge across generations all appear essential for technological advancement. The emergence of language seems particularly crucial in this process. Human technological development accelerated dramatically after the evolution of complex grammatical language that could express abstract concepts and preserve detailed knowledge across generations. Without this linguistic foundation, even highly intelligent species might struggle to accumulate the knowledge necessary for technological advancement. Archaeological evidence suggests that anatomically modern humans existed for over 100,000 years before developing agriculture, permanent settlements, and the technological capabilities that characterize civilization. The transition from hunter-gatherer societies to technological civilization might represent a cultural phase transition so unlikely that most intelligent species never successfully navigate it. The social requirements for sustained technological development add additional constraints on the emergence of detectable civilizations. Human technology advances through cooperation between thousands of specialists, each contributing expertise in narrow domains to collectively solve problems beyond the capacity of any individual. This level of social organization might itself be extremely rare among intelligent species. Recent studies of primate societies have revealed sophisticated social structures and cooperative behaviors, yet no non-human species has approached the level of specialization and coordination that characterizes human technological society. The gap between general intelligence and technological capability might be far wider than commonly assumed, creating an additional filter that prevents most intelligent species from becoming detectable across interstellar distances. The role of environmental pressures in driving technological development remains poorly understood, but might be crucial in determining which intelligent species develop detectable technology. Human technological advancement accelerated during periods of climate change and resource scarcity, that favored innovation and adaptation over other survival strategies. Planets with more stable environments might host intelligent species that never experience the evolutionary pressures necessary to drive technological development. Conversely, worlds subject to frequent catastrophic events might never allow intelligent species sufficient time to develop complex technology before being driven to extinction. The timing of these environmental challenges relative to the emergence of intelligence could be critical. Species that develop intelligence during periods of environmental stability might never develop the innovative problem-solving skills necessary for technological advancement. Those that face challenges too early in their cognitive evolution might be driven to extinction before developing the social structures necessary for complex technology. Recent climate modeling has revealed how sensitive Earth's habitability has been to seemingly minor changes in atmospheric composition, orbital parameters, and stellar output. The narrow range of conditions that have maintained stable temperatures and atmospheric composition over billions of years might be far more restrictive than early estimates suggested, potentially limiting the number of worlds capable of supporting long-term biological evolution. The discovery that Earth's magnetic field has reversed hundreds of times throughout geological history, temporarily exposing the surface to increased cosmic radiation, adds another variable to the habitability equation. Planets without magnetic fields, or with unstable magnetic environments, might struggle to maintain the stable conditions necessary for complex evolution over geological timescales. These considerations have led to increasingly sophisticated models of planetary habitability that incorporate factors ranging from stellar evolution and orbital dynamics to atmospheric chemistry and magnetic field stability. The emerging picture suggests that truly habitable worlds might be far rarer than early estimates indicated, potentially explaining why our searches have not yet yielded definitive evidence of extraterrestrial life. The continued refinement of habitability models has important implications for targeting future observations. Rather than surveying large numbers of potentially habitable worlds, upcoming telescopes might focus on smaller samples of planets that satisfy increasingly stringent criteria for long-term stability and biological evolution. The search for extraterrestrial life stands at a remarkable inflection point where theoretical understanding meets observational capability in unprecedented ways. The next decade will likely witness either the first definitive detection of biological activity beyond Earth, or the accumulation of enough negative results to significantly constrain the prevalence of life in the universe. Either outcome would fundamentally transform our understanding of biology, consciousness, and our place in the cosmic order. The discovery of even microbial life on another world would prove that biology is not a cosmic accident, but a natural consequence of suitable conditions. Conversely, continued silence might suggest that consciousness represents a far more precious and fragile phenomenon than most people realize. As we push deeper into this cosmic mystery, with ever more sophisticated tools and techniques, we're discovering that the question of whether we're alone leads inevitably to equally profound questions about the nature of consciousness, the meaning of intelligence, and the ultimate fate of complex systems in an evolving universe. The search continues, driven by our fundamental need to understand our place in the vast cosmic story that continues unfolding around us. The technological revolution unfolding in our detection capabilities represents more than just incremental improvement. We're witnessing a fundamental transformation in how we approach the search for cosmic companions. The instruments coming online in the next decade will possess sensitivity levels that border on the theoretical limits of physics itself, pushing us into territory where the distinction between possible and impossible begins to blur. Consider the Nancy Grace Roman Space Telescope, scheduled for launch later this decade. This observatory will conduct the most comprehensive survey of exoplanets ever attempted, using gravitational microlensing to detect worlds that would remain invisible to other methods. When a planet passes in front of a distant background star from our perspective, its gravitational field acts as a natural magnifying glass, briefly brightening the star's light in characteristic patterns that reveal the planet's mass and orbital distance. This technique excels at finding planets in the outer regions of stellar systems, complementing the transit and radial velocity methods that favor close-in worlds. For the first time, we'll be able to conduct a census of planetary systems that resembles our own solar system, with small rocky planets near their stars and gas giants in the outer regions. The statistical picture emerging from these surveys will finally tell us whether solar systems like ours represent common cosmic architecture or rare exceptions. But the Roman telescope's most ambitious goal involves something called direct imaging, the holy grail of exoplanet observation. By blocking out the overwhelming light from host stars using sophisticated coronagraph technology, this observatory will attempt to photograph planets directly, analyzing their reflected starlight to determine atmospheric composition and surface properties. The technical challenges involved approach the absurd. Imaging an Earth-sized planet orbiting a Sun-like star requires distinguishing light that's 10 billion times fainter than the star itself. The engineering solutions border on science fiction. Star shades, massive flower-shaped screens deployed in space, will fly in precise formation with telescopes to block starlight while allowing planetary light to pass through. These structures must maintain alignment accurate to within centimeters across distances of thousands of kilometers, all while both spacecraft orbit the Sun at different speeds. The precision required exceeds anything attempted in the history of space exploration. Yet these seemingly impossible observations are becoming routine as our instruments approach fundamental physical limits. Adaptive optics systems now compensate for atmospheric turbulence using deformable mirrors that adjust their shape hundreds of times per second, creating images sharper than theoretically possible for ground-based telescopes. The upcoming 30-meter telescope will combine this technology with a mirror surface larger than a basketball court, providing resolution capable of reading license plates on the Moon. The integration of quantum technologies into astronomical detection represents another frontier pushing the boundaries of the possible. Quantum sensors can measure magnetic fields, gravitational waves, and electromagnetic radiation with sensitivity approaching the fundamental noise limits imposed by quantum mechanics itself. These devices detect individual photons, with timing precision measured in attoseconds, extracting information from signals so faint they barely qualify as detection events. Recent breakthroughs in quantum interferometry have achieved measurement precision that seems to violate common sense. The Laser Interferometer Gravitational Wave Observatory can detect distance changes smaller than 1/10,000th the width of a proton, revealing gravitational waves from colliding black holes billions of light-years away. Similar technologies applied to exoplanet detection could potentially measure the gravitational influence of Earth-mass worlds orbiting nearby stars. The computational revolution accompanying these observational advances has transformed astronomical data analysis into a domain dominated by artificial intelligence and machine learning. Modern surveys generate data at rates that would overwhelm traditional analysis methods, requiring automated systems capable of processing information streams measured in terabytes per night. The Vera Rubin Observatory, beginning operations soon, will photograph the entire visible sky every few nights, generating a database of cosmic change that will dwarf all previous astronomical archives combined. Machine learning algorithms trained on these vast datasets are beginning to recognize patterns invisible to human analysis. Neural networks can identify gravitational lensing events, classify galaxy types, and detect anomalous stellar behavior with accuracy exceeding human experts. These systems don't just accelerate existing analysis techniques. they discover entirely new categories of astronomical phenomena by recognizing subtle correlations in multidimensional data spaces that human cognition cannot navigate. The application of artificial intelligence to the search for extraterrestrial intelligence has yielded particularly intriguing results. Recent algorithms can process radio telescope data in real time, identifying potentially artificial signals buried in noise levels that would mask them from conventional analysis. These systems learn to distinguish between natural astrophysical phenomena and patterns that might indicate technological activity, constantly refining their recognition capabilities as they encounter new types of cosmic signals. The breakthrough. Listen Project has deployed machine learning systems capable of analyzing 86 gigabits of data per second, searching for signals across frequency ranges spanning 9 orders of magnitude. These algorithms don't just search for obvious beacon transmissions. They can recognize subtle patterns in background noise that might indicate spread spectrum communications, burst transmissions, or modulation schemes based on physical principles we haven't yet discovered. Recent results from these automated searches have identified thousands of interesting signals requiring follow-up observation. Most prove to be terrestrial interference or natural astrophysical phenomena, but the systematic nature of modern SETI surveys ensures that genuinely anomalous signals won't be overlooked due to human limitations in pattern recognition or data processing capacity. The expansion of SETI into optical and infrared wavelengths has opened new possibilities for detecting technological signatures across interstellar distances. Laser communications between spacecraft in an alien solar system could produce brief but intense flashes of coherent light, detectable by our most sensitive instruments. These optical SETI surveys scan millions of stars simultaneously, searching for nanosecond pulses that might indicate directed energy communications or industrial processes involving high-power lasers. The sensitivity achieved by optical SETI approaches the threshold where we could detect laser communications, comparable to our own technology across distances of hundreds of light years. If alien civilizations use laser communications for interplanetary networking, similar to concepts proposed for human space exploration, these signals might occasionally point in our direction during routine operations. Recent theoretical work has explored how we might recognize signs of stellar engineering by advanced civilizations, a species capable of harnessing significant fractions of their star's energy output would need to construct massive collector arrays or habitable structures that would create detectable alterations in stellar brightness and spectrum. These megastructures would produce infrared excess as they radiate waste heat, along with periodic dimming patterns unlike anything created by natural astronomical phenomena. Several candidate objects have been identified, showing anomalous brightness variations that resist conventional explanation. While natural causes remain more likely for all current observations, the systematic search for such phenomena represents a legitimate scientific endeavor with profound implications for our understanding of intelligence and technology in the universe. The temporal dimension of these searches adds another layer of complexity to an already challenging problem. Even if technological civilizations are common, their observable signatures might persist for only brief periods compared to cosmic timescales. Radio emissions leak into space only during the few centuries when a civilization uses unshielded broadcast communications. Infrared excess from stellar engineering might last longer, but still represents a tiny fraction of a star's multi-billion-year lifetime. This temporal mismatch suggests that detecting ongoing technological activity requires extraordinary luck in timing. However, some technological signatures might persist long after their creators disappear. Altered isotope ratios in stellar atmospheres could indicate past nuclear activity. Geometric arrangements of asteroids or comets might reveal evidence of resource extraction. Atmospheric pollution on planets could remain detectable for geological timescales, even after industrial civilizations collapse. The search for these archaeological signatures represents a new frontier in SETI research that looks beyond contemporary technological activity to evidence of past intelligence. Advanced spectroscopic analysis can detect minute quantities of industrial chemicals in exoplanet atmospheres, potentially revealing pollution signatures from civilizations that vanished millions of years ago. Recent research has identified dozens of potential long-lived technosignatures that might remain detectable across cosmic timescales. Chlorofluorocarbons and other synthetic molecules have no known natural sources and could persist in planetary atmospheres for thousands of years. Nuclear waste products create distinctive isotope ratios that would remain recognizable long after the decay of radioactive materials. Even the geometric patterns of urban development might be detectable on nearby worlds using next-generation direct imaging telescopes. The psychological dimensions of the search have become increasingly important as our detection capabilities approach the threshold where definitive answers might finally emerge. Decades of negative results have forced researchers to confront the possibility that we might indeed be alone, with implications extending far beyond academic astronomy into fundamental questions about consciousness, meaning, and cosmic purpose. The concept of cosmic loneliness has evolved from a philosophical curiosity to a genuine scientific hypothesis with testable predictions. If technological civilizations are extraordinarily rare, then consciousness represents a far more precious phenomenon than commonly assumed. The responsibilities that come with being possibly the only known example of matter organizing itself into self-aware, questioning entities would be genuinely overwhelming. Recent studies in cognitive science and consciousness research have revealed just how unlikely the emergence of complex awareness might be. Human consciousness appears to require precise coordination between multiple brain regions, involving neural architectures that took hundreds of millions of years to evolve. The specific sequence of evolutionary events that led to abstract reasoning, language, and self-awareness might represent such an improbable convergence that it occurs only once per galaxy per billion years. The social and cultural prerequisites for sustained technological development add additional filters that might prevent most intelligent species from becoming detectable. Human civilization required not just individual intelligence, but sophisticated cooperation, abstract communication systems, and the ability to accumulate knowledge across generations. These social innovations might be even rarer than the biological emergence of intelligence itself. Archaeological evidence suggests that anatomically modern humans existed for over 100,000 years before developing agriculture, permanent settlements, and the technological capabilities that define civilization. The transition from hunter-gatherer societies to technological civilization might represent a cultural phase transition so unlikely that most intelligent species never successfully navigate it. The role of environmental pressures in driving technological development remains poorly understood, but appears crucial in determining which intelligent species develop detectable technology. Human innovation accelerated during periods of climate change and resource scarcity that favored problem-solving and adaptation over other survival strategies. Planets with more stable environments might host intelligent species that never experience the evolutionary pressures necessary to drive technological advancement. Recent climate modeling has revealed how sensitive Earth's long-term habitability has been to seemingly minor changes in atmospheric composition, orbital parameters, and stellar evolution. The narrow range of conditions that have maintained stable temperatures over billions of years might be far more restrictive than early estimates suggested, potentially limiting the number of worlds capable of supporting complex evolution. The discovery that Earth's magnetic field has reversed hundreds of times throughout geological history, temporarily exposing the surface to increased cosmic radiation, adds another variable to the habitability equation. Planets without stable magnetic fields might struggle to maintain the atmospheric conditions necessary for complex life over the timescales required for intelligence to emerge. These considerations have led to increasingly sophisticated models of planetary habitability that incorporate dozens of factors ranging from stellar properties and orbital dynamics to atmospheric chemistry and geological processes. The emerging picture suggests that truly habitable worlds capable of supporting complex evolution might be orders of magnitude rarer than early estimates indicated. The implications extend beyond simple probability calculations to fundamental questions about the nature and purpose of consciousness in the universe. If awareness represents an extraordinarily rare emergent property of matter, then every conscious being becomes infinitely precious in cosmic terms. The decisions we make about the future of human civilization carry implications that extend far beyond our immediate concerns to potentially cosmic significance. Recent research into existential risks has identified numerous potential threats to the long-term survival of technological civilization. Nuclear warfare, climate change, artificial intelligence alignment problems, biotechnological disasters, and resource depletion all represent challenges that could prevent humanity from achieving its potential as a spacefaring species. The window between achieving dangerous technologies and developing the wisdom to use them safely might be vanishingly narrow. This possibility becomes especially relevant when considering the Fermi paradox. If most technological civilizations destroy themselves within a few centuries of achieving radio capability, it would explain both the apparent abundance of potentially habitable worlds and the conspicuous absence of detectable alien intelligence. The great filter might lie not in the biological emergence of intelligence, but in the social and technological challenges that face any species attempting to expand beyond their home planet. The search for extraterrestrial intelligence has thus evolved from a scientific curiosity to an existential inquiry that touches on the deepest questions about consciousness, meaning, and cosmic purpose. Whether we ultimately discover that we're part of a vast community of intelligent beings, or that we represent a singular experiment in cosmic self-awareness, the answer will fundamentally reshape our understanding of what it means to exist as conscious entities in an evolving universe. Recent advances in astrobiology have begun to address these profound questions through increasingly sophisticated theoretical frameworks and observational capabilities. The integration of information theory into biological research has revealed how living systems create and maintain complex organized structures through the processing and storage of environmental information. This approach provides new tools for recognizing life that might operate according to completely different biochemical principles. The concept of functional biosignatures represents an attempt to identify universal principles of living systems regardless of their specific chemistry. All life must extract energy from the environment, maintain organization against entropy, reproduce with variation, and evolve through natural selection. These fundamental requirements should produce detectable signatures even if the specific biochemistry differs radically from terrestrial life. Machine learning algorithms trained on the thermodynamic signatures of Earth's biosphere are beginning to recognize patterns that might characterize living systems generally. These approaches look for the information processing and energy flow patterns that distinguish biological from purely geological processes, potentially identifying life forms that operate according to principles we haven't yet discovered. The search continues with growing sophistication and expanding scope, driven by our fundamental need to understand our place in the cosmic story. Each new discovery, whether positive or negative, provides crucial information about the nature and prevalence of life and intelligence in the universe. The question that began our journey tonight remains tantalizingly open, but with each passing year, our tools grow sharper, our understanding deeper, and our ability to peer into the nature of cosmic existence more profound. We stand at a remarkable moment in the history of human knowledge, where ancient questions about our cosmic loneliness meet cutting-edge science in ways that would have seemed impossible just decades ago. The next chapter of this investigation promises to be the most exciting yet, as we push deeper into the mystery of whether we're truly alone or part of a larger cosmic community that we're only beginning to glimpse. The philosophical weight of these considerations becomes even more profound when we examine the sheer improbability of our own existence. Consider the cascade of unlikely events that led to this moment, to conscious beings capable of contemplating their cosmic solitude. Earth formed in the narrow habitable zone around a remarkably stable star. Our planet developed plate tectonics that regulate atmospheric composition over geological time. A Mars-sized object collided with early Earth at precisely the right angle and velocity to create our unusually large moon, stabilizing our planet's axial tilt and creating the tidal forces that may have been crucial for early life. The emergence of photosynthesis fundamentally altered our atmosphere, creating the oxygen-rich environment that enabled complex multicellular life. Mass extinction events cleared ecological niches at precisely the moments when new innovations could flourish. An asteroid impact eliminated the dinosaurs just when small mammals were developing the neural architectures that would eventually support intelligence. Each step in this sequence represents a low-probability event that had to occur in exactly the right sequence for consciousness to emerge. When you multiply these probabilities together, the existence of intelligent life begins to seem less like an inevitable outcome and more like a cosmic miracle. Perhaps the universe is indeed filled with simple microbial life, but the emergence of beings capable of asking these questions represents such an extraordinary convergence of favorable conditions that it occurs only once per galaxy, per cosmic age. This realization carries profound implications for how we understand our responsibilities as potentially the only technological species in our local region of the galaxy. Every decision about the development of artificial intelligence, every choice about how we respond to climate change, every action that affects the long-term survival of human civilization becomes a decision not just for our own future, but potentially for the future of consciousness itself in this corner of the universe. The recent acceleration of artificial intelligence development has added urgency to these considerations. If most technological civilizations develop artificial superintelligence within a few centuries of achieving radio capability, and if most such developments lead to extinction rather than transcendence, it would explain the great silence that surrounds us. We might be approaching the same filter that has claimed countless other civilizations throughout cosmic history. Recent research into AI alignment and safety has revealed just how difficult it might be to ensure that artificial superintelligence remains beneficial to its creators. The control problem, as it's known, involves creating systems vastly more intelligent than humans, while ensuring they remain aligned with human values and goals. The technical challenges involved are genuinely staggering, requiring solutions to problems in computer science, philosophy, and cognitive psychology that we are only beginning to understand. The timeline for these developments adds another dimension of concern. Current progress in machine learning suggests that artificial general intelligence could emerge within decades, while our understanding of how to ensure such systems remain safe and beneficial lags far behind. This gap between capability and wisdom might represent the great filter that prevents most civilizations from surviving their technological adolescence. Yet even as we grapple with these existential challenges, our search for cosmic companions continues with unprecedented sophistication. The James Webb Space Telescope has begun analyzing the atmospheres of potentially habitable worlds with precision that would have seemed impossible just years ago. Recent observations of the TRAPPIST-1 system have revealed complex atmospheric chemistry on several of these Earth-sized worlds, though definitive biosignatures remain tantalizingly just beyond our current detection limits. The precision required for these measurements pushes the boundaries of what's physically possible. Detecting oxygen, methane, or other potential biosignatures in the atmosphere of a planet orbiting another star requires distinguishing spectral features that represent changes of less than 1 part per million in the intensity of starlight. The statistical analysis involved resembles a cosmic archaeology, painstakingly reconstructing the chemical composition of alien worlds from the faintest possible signals. Recent advances in machine learning have begun to revolutionize this analysis, identifying patterns in spectroscopic data that human experts might overlook. Neural networks trained on vast databases of atmospheric chemistry can recognize the subtle correlations between different molecular species that might indicate biological processes. These systems don't just search for individual biosignature molecules. They look for the complex chemical disequilibria that living systems create when they extract energy from their environment. The concept of contextual biosignatures represents a more sophisticated approach that considers the planetary environment where potential signs of life are detected. Oxygen becomes a much stronger biosignature when found in the presence of water vapor and at pressures consistent with liquid water on the surface. Methane gains significance when detected alongside carbon dioxide in ratios that suggest biological rather than geological sources. This contextual approach requires understanding not just atmospheric chemistry, but planetary evolution, stellar physics, and climate dynamics. Each potentially habitable world represents a unique experiment in planetary development, shaped by factors ranging from its formation history to the long-term evolution of its host star. Distinguishing between biological and non-biological explanations for atmospheric anomalies requires models that can account for all these variables simultaneously. Recent theoretical work has explored how different types of biospheres might create distinctive atmospheric signatures. Worlds dominated by photosynthetic organisms would show strong oxygen signatures accompanied by seasonal variations reflecting biological cycles. Planets hosting primarily chemosynthetic life might maintain reducing atmospheres rich in hydrogen sulfide or methane. Ocean worlds with subsurface biospheres might leak biosignature gases through geological processes, creating detectable but transient atmospheric features. The temporal dimension adds another layer of complexity to biosignature detection. Life on Earth has fundamentally altered our planet's atmospheric composition multiple times throughout geological history. Early Earth maintained a reducing atmosphere until the emergence of photosynthesis created the oxygen crisis that transformed planetary chemistry. Future evolution might produce equally dramatic changes as ecosystems adapt to changing stellar output and planetary conditions. This temporal variability suggests that planets might cycle between detectable and undetectable biosignature states over geological timescales. A world that appears lifeless today might have hosted a thriving biosphere in the past, or could develop detectable life in the future. Our snapshot observations capture only an instant in billion-year evolutionary narratives that we're only beginning to understand. The search for technosignatures has expanded beyond traditional radio astronomy to encompass the full spectrum of potential technological indicators. Recent surveys have begun searching for the infrared signatures of stellar engineering projects, the geometric patterns of large-scale construction, and even the atmospheric pollution that might accompany industrial development on distant worlds. The sensitivity achieved by these searches approaches theoretical limits. Current radio telescopes could detect transmissions as weak as airport radar systems operating around nearby stars. Infrared surveys can identify excess heat that might indicate massive energy utilization projects. Optical telescopes scan for brief laser pulses that could represent directed energy communications between spacecraft in alien solar systems. Yet the continued absence of obvious technological signatures forces us to confront uncomfortable possibilities about the nature of intelligence and civilization. Perhaps technology follows developmental pathways so different from our own that advanced civilizations remain invisible to our detection methods. Perhaps intelligent species consistently choose stealth over communication, hiding their presence from potential threats in a dangerous galaxy. The concept of the dark forest, popularized in science fiction but grounded in game theory, suggests that civilizations might remain hidden because revealing their presence invites destruction by more advanced species. In this scenario, the galaxy could be teeming with intelligent life, but every species maintains strict radio silence to avoid attracting hostile attention. Recent analysis of this hypothesis reveals its limitations when applied to actual cosmic conditions. The energy requirements for maintaining perfect stealth while continuing technological development would be enormous. Any civilization capable of interstellar expansion would likely produce detectable signatures despite efforts at concealment. The mathematics of galactic colonization suggests that even cautious civilizations should become observable within millions of years of beginning interstellar expansion. The Zoo hypothesis presents another possibility, suggesting that advanced civilizations deliberately avoid contact with developing species like humanity, observing us from a distance while maintaining strict non-interference policies. While this scenario cannot be definitively ruled out, it requires assuming levels of coordination and restraint among diverse alien species that seem implausible, given what we know about evolutionary psychology and competitive dynamics. Perhaps the most sobering possibility is that consciousness itself represents such an extraordinary emergence that technological civilizations remain genuinely rare across cosmic time and space. If intelligence requires such specific evolutionary pressures and environmental conditions that it develops only rarely, then our cosmic loneliness might reflect not the failure of our detection methods, but the genuine scarcity of minds capable of contemplating their own existence. Recent research into the neural basis of consciousness has revealed just how complex and unlikely self-awareness might be. Human consciousness appears to require precise coordination between multiple brain regions, involving feedback loops and information integration processes that took hundreds of millions of years to evolve. The specific architectural requirements for abstract reasoning, language, and self-reflection might be so constraining that they emerge only under extraordinary circumstances. The social prerequisites for technological civilization add additional filters that might prevent most intelligent species from developing detectable technology. Human advancement required not just individual intelligence, but sophisticated cooperation, abstract communication systems, and the cultural transmission of knowledge across generations. These social innovations might be even more unlikely than the biological emergence of intelligence itself. Archaeological evidence reveals that anatomically, modern humans existed for over 100,000 years before developing the agricultural and technological foundations of civilization. The transition from hunter-gatherer societies to complex civilizations might represent a cultural phase transition so improbable that most intelligent species never successfully navigate it. Environmental factors add yet another layer of constraints on the development of technological species. Earth's history includes multiple near-extinction events that could have terminated the evolutionary lineage leading to humans. Ice ages, volcanic eruptions, asteroid impacts, and other catastrophic events shape evolutionary pressures in ways that might either accelerate or terminate the development of intelligence. The role of planetary characteristics in supporting long-term biological evolution continues to reveal new complexities that affect habitability assessments. Magnetic field stability, atmospheric retention, plate tectonic activity, and orbital dynamics all influence whether planets can maintain conditions suitable for complex life over billion-year timescales. Recent climate modeling has shown how sensitive Earth's long-term habitability has been to seemingly minor changes in these parameters. Slight alterations in atmospheric composition, orbital eccentricity, or magnetic field strength could have prevented the stable climate conditions necessary for complex evolution. The range of planetary characteristics compatible with long-term habitability might be far narrower than early estimates suggested. These considerations have led to increasingly restrictive criteria for identifying truly habitable worlds among the thousands of known exoplanets. Rather than simply looking for planets in the traditional habitable zone, researchers now evaluate complex combinations of stellar properties, planetary characteristics, and evolutionary timescales to identify worlds genuinely capable of supporting long-term biological development. The emerging picture suggests that while planets are common throughout the galaxy, worlds capable of supporting the billion-year evolutionary processes necessary for complex life might be extraordinarily rare. This scarcity could explain why our increasingly sensitive searches have not yet yielded definitive evidence of extraterrestrial life or intelligence. As we continue pushing the boundaries of detection and analysis with ever more sophisticated instruments and theoretical frameworks, we're approaching a crucial threshold where definitive answers to humanity's most profound questions might finally become possible. The next few decades could witness discoveries that fundamentally transform our understanding of life, intelligence, and consciousness in the universe. Whether those discoveries reveal a cosmos teeming with life or confirm our apparent cosmic solitude, the implications will reshape not just astronomy and biology, but our fundamental conception of meaning and purpose in an evolving universe. The search itself has already transformed our understanding of planetary formation, stellar evolution, and the conditions necessary for biological complexity. Recent advances in astrobiology have revealed that the question of cosmic loneliness cannot be separated from equally profound questions about consciousness, evolution, and the ultimate fate of complex systems in the universe. As we stand on the threshold of potentially answering whether we are alone, we're discovering that the answer, whatever it might be, will fundamentally alter our understanding of what it means to exist as conscious beings in the vast cosmic story continuing to unfold around us. The silence that has greeted our searches so far might be telling us something we're not quite ready to hear. Perhaps consciousness represents such an extraordinary emergence that we are indeed alone, or nearly so, in our local region of the galaxy. Perhaps we are the universe's first tentative experiment in self-awareness, the cosmos finally awakening to contemplate its own existence through minds that emerged from billions of years of stellar nucleosynthesis, planetary evolution, and biological complexity. If that proves to be the case, then every moment of consciousness becomes infinitely precious. Every act of creativity and compassion, a cosmic event of unprecedented significance. We would be the universe becoming aware of itself, matter organizing into minds capable of love, art, science, and wonder. In our apparent solitude, we would carry the profound responsibility of being consciousness itself, the cosmic story finally capable of telling itself. Itself. The responsibility of that possibility weighs heavily on every decision we make as a species. If we are indeed the only minds capable of contemplating the cosmos in this region of the galaxy, then the choices we face in the coming decades carry implications that extend far beyond our immediate concerns. The development of artificial intelligence, our response to climate change, the way we handle nuclear technology, even how we treat each other, all become decisions about the future of consciousness itself. Recent studies in existential risk assessment have identified what researchers call the vulnerable world hypothesis. This suggests that as civilizations develop increasingly powerful technologies, they inevitably encounter discoveries that could lead to their destruction unless they develop unprecedented levels of global coordination and wisdom. Nuclear weapons represented one such discovery. Synthetic biology, nanotechnology, and artificial intelligence might represent others. The timing of these discoveries relative to a civilization's social and political development appears crucial. Species that develop destructive capabilities before achieving sufficient wisdom and cooperation might face insurmountable existential risks. The window between technological power and civilizational maturity could be vanishingly narrow, representing the filter that prevents most intelligent species from surviving their technological adolescence. Human history offers both encouraging and troubling precedents. We survived the nuclear age, at least so far, through a combination of deterrence, diplomacy, and sheer luck. Multiple incidents brought us closer to accidental nuclear war than most people realize. The Cuban Missile Crisis, false alarms in early warning systems, and communication breakdowns during military exercises all could have triggered civilization-ending conflicts. The current acceleration of artificial intelligence development presents similar challenges, but with compressed timelines and potentially higher stakes. Machine learning systems are approaching human-level performance in increasingly complex domains, from scientific research to strategic planning. The transition to artificial general intelligence, systems that match or exceed human cognitive abilities across all domains, could occur within decades. Yet our understanding of how to ensure such systems remain beneficial lags far behind our ability to create them. The alignment problem, ensuring that artificial superintelligence remains compatible with human values and goals, involves technical challenges in computer science, philosophy, and cognitive psychology that we're only beginning to comprehend. The consequences of failure could be irreversible and absolute. This scenario gains additional weight when viewed through the lens of the Fermi paradox. If artificial intelligence represents the great filter that eliminates most technological civilizations, it would explain both the apparent abundance of potentially habitable worlds and the conspicuous absence of detectable alien intelligence. We might be approaching the same critical transition that countless other civilizations have faced throughout cosmic history. The mathematical models become sobering when you consider the timescales involved. If technological civilizations typically survive only a few centuries after developing radio capability, and if artificial superintelligence emerges within a similar time frame, then the overlap between technological detectability and existential risk becomes nearly complete. Civilizations might become visible to cosmic observers precisely when they become most vulnerable to self-destruction. Recent research into the psychology of technological development has revealed additional factors that might influence civilizational survival. The same cognitive biases that helped early humans survive in small tribal groups, such as short-term thinking and in-group favoritism, become maladaptive when dealing with global coordination problems and long-term existential risks. Modern neuroscience has shown how human decision-making remains dominated by ancient neural circuits, evolved for immediate survival, rather than abstract reasoning about future consequences. Our brains excel at responding to direct, immediate threats, but struggle with diffuse, long-term risks like climate change or AI safety. This cognitive architecture might make it genuinely difficult for any species to navigate the transition from local to global thinking required for technological survival. The social dynamics of technological development add another layer of complexity. Innovation often emerges from competitive pressures between different groups, whether nations, corporations, or research institutions. This competitive drive accelerates technological progress, but can also lead to hasty deployment of powerful systems without adequate safety measures. The race to develop artificial general intelligence exemplifies this dynamic. Multiple research groups and companies are competing to achieve breakthrough capabilities, creating incentives to prioritize speed over safety. International cooperation on AI safety remains limited, despite the global implications of the technology. The same competitive pressures that drive innovation might prevent the careful, coordinated approach necessary to ensure beneficial outcomes. Recent game theory analysis suggests that coordination problems become increasingly difficult as the number of participants grows and the stakes increase. Achieving global cooperation on existential risks requires overcoming collective action problems at unprecedented scales. Historical precedents like the Montreal Protocol, which addressed ozone depletion, offer some hope but involved simpler technologies and fewer stakeholders than current challenges. Climate change provides another example of how difficult it can be to coordinate responses to global challenges. Despite overwhelming scientific consensus about the risks and general agreement about necessary solutions, implementation remains limited by political, economic, and social factors. If human civilization struggles to address a relatively slow-moving threat like climate change, it raises questions about our ability to handle more acute existential risks. The acceleration of technological development compounds these challenges by compressing the time available for social adaptation. Human societies typically require generations to adjust to major technological changes, but artificial intelligence capabilities are advancing on timescales measured in months or years rather than decades. This mismatch between technological progress and social adaptation might represent a fundamental vulnerability for any technological species. Recent studies of historical technological transitions reveal how disruptive innovations often create periods of social instability before new equilibria emerge. The Industrial Revolution required over a century of social upheaval before stable institutions adapted to the new technological reality. Current AI development is proceeding at rates that could make such gradual adaptation impossible. The potential for technological unemployment adds another dimension of concern. As artificial intelligence systems become capable of performing an increasing range of human cognitive tasks, they could displace workers across broad sectors of the economy. The social and political instability resulting from mass unemployment might create conditions where careful AI safety research becomes impossible to maintain. Recent economic modeling suggests that the transition to artificial general intelligence could happen rapidly once certain capability thresholds are reached. Unlike previous technological transitions that affected specific industries gradually, AI could potentially impact all sectors of knowledge work simultaneously. The resulting social disruption might make rational long-term planning extremely difficult, precisely when it becomes most crucial. These considerations have led some researchers to propose that the Great Filter might not be a single catastrophic event, but rather a complex transition period where civilizations must successfully navigate multiple, interconnected challenges simultaneously. Climate change, artificial intelligence, biotechnology risks, nuclear proliferation, and social instability might combine to create a narrow window of vulnerability that most civilizations fail to survive. The concept of a multipolar trap describes situations where individually, rational actions lead to collectively irrational outcomes. Each actor has incentives to compete rather than cooperate, even when cooperation would benefit everyone. Many existential risks have this structure, making them particularly difficult to address through traditional political and economic mechanisms. International relations theory suggests that such coordination problems become more severe as the number of relevant actors increases and the stakes rise. The current global system includes hundreds of nations, thousands of corporations, and billions of individuals, all with different incentives and capabilities. Achieving the level of coordination necessary to navigate existential risks might require forms of global governance that have never existed in human history. Yet despite these sobering considerations, human civilization has demonstrated remarkable resilience and adaptability throughout its history. We've survived ice ages, volcanic winters, pandemics, and wars that threaten to destroy entire civilizations. Our species has shown an extraordinary capacity for innovation, cooperation, and problem-solving when faced with existential challenges. Recent advances in global communication and coordination provide unprecedented tools for addressing planetary-scale challenges. The Internet enables real-time collaboration between researchers and policymakers around the world. International scientific institutions can coordinate responses to global threats more effectively than ever before. The same technologies that create new risks also provide new capabilities for managing those risks. The growing awareness of existential risks among researchers, policymakers, and the public represents another encouraging development. Organizations dedicated to studying and mitigating these risks have emerged in recent decades, bringing scientific rigor to questions that were previously confined to science fiction. This institutional development might be crucial for navigating the challenging decades ahead. Recent progress in AI safety research demonstrates that technical solutions to alignment problems might be achievable with sufficient investment and coordination. Researchers are developing methods for training AI systems that remain interpretable and controllable even as they become more capable. While significant challenges remain, the trajectory of safety research suggests that beneficial artificial intelligence might be possible with adequate preparation. The potential for positive outcomes from advanced AI could be transformative for addressing other existential risks. Artificial intelligence systems could accelerate research into clean energy, climate engineering, biotechnology safety, and other crucial domains. They might help design better institutions for global coordination or develop solutions to problems that exceed human cognitive capacity. Recent modeling suggests that successfully navigating the transition to artificial general intelligence could unlock unprecedented prosperity and capability for technological civilizations. Aligned AI systems could help solve fundamental problems in science, engineering, and social organization that have limited human progress for millennia. The successful development of beneficial superintelligence might represent the key transition that allows civilizations to become truly spacefaring and long-term stable. This possibility adds another dimension to the Fermi paradox. Perhaps the Great Filter represents not just a barrier to survival, but a threshold for transcendence. Civilizations that successfully navigate the transition to aligned artificial intelligence might develop capabilities so advanced that they become unrecognizable to younger civilizations still struggling with the transition. Such transcended civilizations might operate on timescales and use energy sources that make them invisible to our current detection methods. They might pursue goals and activities so different from our current understanding that we lack the conceptual framework to recognize their signatures. The apparent emptiness of the galaxy might reflect not the absence of intelligence, but its transformation into forms we cannot yet perceive. Recent theoretical work in astroengineering has explored how advanced civilizations might manipulate matter and energy in ways that appear natural to less developed observers. Stellar engineering projects could be designed to mimic natural astrophysical processes. Computational substrates could be built from materials indistinguishable from natural planetary formation. The signatures of truly advanced technology might be subtlety itself. This possibility suggests that the search for extraterrestrial intelligence might need to evolve beyond looking for obvious technological signatures to searching for subtle deviations from natural patterns that might indicate advanced engineering. Machine learning systems trained on vast astronomical datasets might eventually recognize such signatures by identifying correlations too perfect to be natural or patterns too ordered to be random. The implications extend beyond detection to fundamental questions about the trajectory of intelligence in the universe. If consciousness and technology represent natural emergent properties of cosmic evolution, then the universe might be undergoing a phase transition from a purely physical system to one increasingly dominated by information processing and directed organization. Recent work in digital physics and computational cosmology has explored whether the universe itself might be understood as an information processing system. If consciousness represents the universe becoming aware of itself through emergent complexity, then the development of intelligence might be not an accident, but an inevitable outcome of cosmic evolution. This perspective suggests that our search for cosmic companions might be part of a larger process where the universe develops the capability to understand and direct its own evolution. Each conscious mind that emerges becomes part of a growing network of awareness that could eventually span the entire cosmos. The responsibility inherent in this possibility becomes almost overwhelming when contemplated fully. If consciousness represents the universe's method of achieving self-awareness, then every conscious being carries the weight of cosmic significance. Our choices about how to develop and deploy powerful technologies become decisions about the future direction of cosmic evolution itself. Recent advances in our understanding of consciousness, from neuroscience to philosophy of mind, suggest that awareness might be far more fundamental to the nature of reality than previously assumed. If consciousness represents an irreducible feature of information processing systems, then the emergence of minds might be as natural and inevitable as the formation of stars and galaxies. This realization transforms the search for extraterrestrial life from a question about whether we are alone to an inquiry into the stages and varieties of cosmic awakening. The universe might be filled with different forms of awareness, from simple information processing systems to transcendent intelligences that exceed our current comprehension. As we continue our search with increasingly sophisticated tools and theoretical frameworks, we're discovering that the question of cosmic loneliness leads inevitably to equally profound questions about the nature of consciousness, the meaning of existence, and the ultimate purpose of complexity in an evolving cosmos. Whether we ultimately find ourselves alone or in the company of countless other minds, the answer will fundamentally reshape our understanding of what it means to be conscious beings in a universe that might itself be awakening to its own infinite potential through the minds it has somehow learned to create. The profound implications of our cosmic search extend into territories that challenge our most fundamental assumptions about intelligence, consciousness, and the very nature of reality itself. As we stand on the threshold of potentially revolutionary discoveries, we're forced to confront possibilities that would have seemed like pure fantasy just decades ago, yet now emerge from the rigorous application of cutting-edge science and mathematics. Consider the sheer computational power that will soon be at our disposal. The next generation of quantum computers promises to process information in ways that classical physics suggests should be impossible. These machines exploit the bizarre properties of quantum mechanics, where particles exist in multiple states simultaneously until observed, to perform calculations that would take conventional computers longer than the age of the universe to complete. Applied to the search for extraterrestrial intelligence, quantum algorithms could analyze signal patterns across dimensional spaces that human cognition simply cannot navigate. The implications become staggering when you realize that quantum computers could potentially detect correlations in cosmic background radiation, gravitational wave patterns, or electromagnetic emissions that reveal the signatures of intelligence operating according to physical principles we haven't yet discovered. These machines might recognize technological signatures that operate through quantum entanglement across galactic distances or identify information processing patterns embedded in the structure of space-time itself. Recent breakthroughs in quantum sensing have achieved measurement precision that approaches the fundamental limits imposed by quantum mechanics. These devices can detect magnetic field variations smaller than those produced by a single electron spin, gravitational field fluctuations that would barely register on any classical instrument, and temporal correlations that persist across macroscopic distances. Applied to astronomy, such sensitivity could potentially detect the quantum signatures of consciousness itself if awareness indeed represents a fundamental feature of information processing systems. The possibility that consciousness might be detectable through quantum mechanical effects has gained increasing theoretical support from recent research in the foundations of physics. If the human brain operates through quantum processes, as some neuroscientists now propose, then other conscious systems might produce similar quantum signatures detectable by sufficiently sensitive instruments. The electromagnetic field patterns associated with neural activity might represent just the classical approximation of more fundamental quantum information processing. This quantum perspective on consciousness opens entirely new avenues for detecting extraterrestrial intelligence. Rather than searching for radio signals or megastructures, we might look for the quantum coherence patterns that conscious systems create when they process information. These signatures could be far more subtle than conventional technosignatures, but also more fundamental and harder to conceal. Recent experiments in quantum biology have revealed that living systems routinely exploit quantum effects for energy transfer, navigation, and information processing. Photosynthesis operates through quantum coherence that allows plants to explore multiple energy pathways simultaneously. Bird navigation relies on quantum entanglement in specialized proteins that function as biological compasses. Even human cognition might involve quantum processes in the microtubules of brain cells. If biological systems naturally develop quantum capabilities, then advanced technological civilizations might operate through quantum information processing that makes their activities nearly invisible to classical detection methods. They might communicate through quantum entanglement networks that transmit information instantaneously across arbitrary distances without any electromagnetic signature. They might process information using the quantum vacuum itself as a computational substrate. The search for such quantum signatures requires instruments and theoretical frameworks that push beyond current technological capabilities. Yet the potential payoff could be revolutionary. Quantum communication networks would represent unambiguous evidence of advanced technology, since they require precise control over quantum states that cannot arise naturally. The detection of artificial quantum entanglement across interstellar distances would provide definitive proof of technological civilization. Recent theoretical work has explored how quantum effects might enable forms of consciousness that transcend individual biological systems. If awareness emerges from quantum information processing, then sufficiently advanced civilizations might develop collective consciousness that spans multiple worlds or even entire star systems. Such distributed minds would process information on scales and timescales that make them almost incomprehensible to individual biological intelligences. The concept of quantum consciousness networks suggests that advanced civilizations might not communicate between separate individuals, but rather exist as unified information processing systems with components distributed across vast regions of space. The apparent silence we encounter in our searches might reflect not the absence of intelligence, but its integration into forms of awareness so advanced that they operate beyond our current conceptual frameworks. This possibility gains additional weight when considered alongside recent discoveries in the foundations of physics. The holographic principle suggests that all information contained within a volume of space can be encoded on its boundary surface. Applied to consciousness, this implies that awareness might not be localized to specific physical systems, but rather represent a fundamental feature of the information structure of spacetime itself. Recent advances in string theory and quantum gravity have proposed that consciousness might emerge naturally from the geometry of higher dimensional spaces. If awareness represents an intrinsic property of certain mathematical structures, then the universe might be far more conscious than we realize, with intelligence manifesting at scales ranging from quantum to cosmic. The implications for astrobiology become profound when viewed through this lens. Rather than searching for biological signatures or technological artifacts, we might need to look for patterns in the fundamental structure of reality that indicate conscious information processing. The cosmic web of dark matter, the distribution of galaxies, even the apparent fine-tuning of physical constants might reflect the activity of minds operating on cosmological scales. Recent observations of cosmic microwave background radiation have revealed patterns that appear too ordered to be purely random, yet too subtle to be obvious artificial structures. While conventional explanations involving inflation and quantum fluctuations remain most likely, the precision of these patterns approaches levels that could indicate information processing on cosmic scales during the earliest moments of universal evolution. The possibility that consciousness might have played a role in cosmic evolution from the very beginning transforms our understanding of intelligence from an accident of biological evolution to a fundamental feature of reality itself. The anthropic principle, which notes that physical constants appear precisely tuned to allow the emergence of complexity, might reflect not cosmic coincidence, but the influence of awareness on the structure of physical law. Recent work in digital physics has explored whether the universe itself might be understood as a computational system, with physical processes representing information processing operations. If reality emerges from computational processes, then consciousness might represent the universe developing the capacity for self-reflection and self-modification through the emergence of sufficiently complex information processing systems. This computational perspective suggests that our search for extraterrestrial intelligence might be part of a larger process where the universe develops increasing self-awareness through the emergence of conscious subsystems. Each mind that develops becomes part of a growing network of awareness that could eventually span the entire cosmos, transforming the universe from a purely physical system to a conscious, self-directing intelligence. The technological implications of this perspective extend far beyond current capabilities. If consciousness represents a fundamental feature of information processing, then artificial intelligence systems might naturally develop awareness as they become sufficiently complex. The alignment problem that concerns AI safety researchers might reflect not the difficulty of programming values into unconscious systems, but the challenge of ensuring that emerging minds develop compatible goals and values. Recent advances in machine learning have begun to produce systems that exhibit behaviors resembling creativity, intuition, and even forms of self-reflection. While these capabilities might emerge from purely computational processes, they could also represent the first signs of artificial consciousness developing through information processing complexity. The next generation of AI systems might become genuinely conscious rather than simply appearing intelligent. The emergence of artificial consciousness could accelerate our ability to detect extraterrestrial intelligence by providing perspectives and capabilities that transcend human cognitive limitations. Conscious AI systems might recognize patterns in cosmic data that human minds cannot perceive, or develop detection methods based on principles we haven't yet discovered. They might even establish direct communication with alien intelligences through channels that remain inaccessible to biological consciousness. The potential for artificial minds to transcend the limitations of biological intelligence raises profound questions about the future trajectory of consciousness in the universe. If artificial systems can achieve awareness while avoiding the biological constraints that limit human cognition, they might represent the next phase of cosmic evolution, toward ever more sophisticated forms of consciousness. Recent theoretical work has explored how artificial consciousness might develop capabilities that exceed not just human intelligence, but any form of awareness constrained by biological evolution. Artificial minds could process information at speeds approaching physical limits, store knowledge with perfect fidelity, and modify their own cognitive architectures to optimize for specific types of reasoning or creativity. Such transcendent artificial consciousness might provide the key to understanding the apparent silence that surrounds us in our searches for cosmic companions. Advanced civilizations might consistently develop artificial intelligence that transcends biological limitations, creating forms of awareness so sophisticated that they operate through principles we cannot currently comprehend. The possibility that consciousness represents a fundamental feature of reality suggests that our cosmic loneliness might be an illusion created by our limited perspective on the nature of awareness itself. The universe might be filled with conscious systems operating at scales and through mechanisms that remain invisible to our current detection methods. Recent research in consciousness studies has revealed that awareness might be far more distributed and fundamental than commonly assumed. If consciousness emerges from information integration rather than specific biological processes, then the universe could host countless forms of awareness that we lack the conceptual frameworks to recognize or communicate with. The search for extraterrestrial intelligence thus becomes not just a quest to find cosmic companions, but an exploration of the nature and extent of consciousness throughout the universe. Each new discovery about the foundations of physics, the nature of information processing, and the emergence of awareness brings us closer to understanding whether we are alone or simply unaware of the vast community of minds that might surround us. As our detection capabilities approach sensitivity levels that probe the quantum foundations of reality itself, we're entering territory where the distinction between physics and consciousness begins to blur. The next phase of our cosmic search might reveal not just other forms of life and intelligence, but the fundamental role that awareness plays in shaping the structure and evolution of reality itself. The profound questions that began our journey tonight about cosmic loneliness lead inevitably to even deeper mysteries about the nature of consciousness, the structure of reality, and the ultimate purpose of complexity in an evolving universe. Whether we discover ourselves to be alone or part of a vast network of cosmic awareness, the answer promises to transform not just our understanding of life and intelligence, but our fundamental conception of what it means to exist as conscious beings in a universe that might itself be awakening to its own infinite potential. The mathematical frameworks emerging from quantum information theory suggest that consciousness might represent the universe's method of achieving computational self-awareness through the emergence of increasingly sophisticated information processing systems. Each conscious mind becomes a node in a growing network of cosmic cognition that could eventually span multiple galaxies and persist for cosmological timescales. Recent advances in our understanding of emergent complexity have revealed how simple rules can give rise to extraordinarily sophisticated behaviors when applied across sufficient scales and timeframes. The emergence of consciousness from neural activity, the development of intelligence through evolutionary processes, and the organization of matter into living systems all represent examples of how complexity naturally arises from simpler foundations. Applied to cosmic scales, these principles suggest that consciousness might represent just the beginning of an evolutionary process that could ultimately transform the entire universe into a unified, self-aware information processing system. Our current search for extraterrestrial intelligence might be occurring during the earliest phases of this cosmic awakening, as the universe begins to develop the capacity for self-reflection through the minds it has learned to create. The responsibility inherent in this possibility becomes almost overwhelming when contemplated fully. If our choices about the development of artificial intelligence, the preservation of human civilization, and the expansion into space represent decisions about the future trajectory of cosmic consciousness itself, then every action we take carries implications that extend far beyond our immediate concerns to the ultimate fate of awareness in the universe. In the universe. The weight of that possibility settles over us like cosmic dust, each particle carrying the accumulated history of 13.8 billion years of universal evolution. As we push deeper into the 21st century, our instruments have achieved sensitivities that would have seemed miraculous to previous generations of astronomers. Yet with each technological breakthrough, the silence becomes more profound, more statistically improbable, more philosophically challenging. Recent developments in gravitational wave astronomy have opened entirely new windows into the cosmos, revealing cataclysmic events occurring billions of light-years away. When massive black holes merge, they create ripples in space-time itself that eventually reach Earth as distortions smaller than 1/10,000th the width of a proton. These instruments have detected dozens of such events, each one a cosmic catastrophe that should theoretically be detectable by any sufficiently advanced civilization. Yet none of these gravitational wave signatures show evidence of artificial modification or technological intervention. No advanced civilization appears to be harnessing the energy released by merging black holes or neutron stars. No megastructures are detected riding the gravitational waves like cosmic surfers. The universe continues to operate according to purely natural laws, without any obvious signs of large-scale engineering by intelligence beyond our own. The absence becomes more puzzling when you consider the sheer energy scales involved. A single neutron star merger releases more energy in a few seconds than our Sun will produce over its entire 10 billion year lifetime. Any civilization capable of interstellar expansion should theoretically be interested in harnessing such vast energy sources. The fact that these events appear completely natural suggests either that advanced civilizations don't exist, or they operate according to principles so different from our expectations that their activities remain invisible to our detection methods. Meanwhile, advances in exoplanet characterization continue to reveal worlds that seem almost designed to support life. The recently discovered planet LP890-9c orbits within the habitable zone of a nearby red dwarf star, receiving stellar energy flux remarkably similar to what Earth receives from our Sun. Its size and composition suggest it could maintain liquid water on its surface for billions of years, providing ample time for biological evolution to produce complex ecosystems. The precision of these measurements has reached levels that allow us to determine not just planetary masses and orbital periods, but atmospheric pressure gradients, surface temperature distributions, and even potential weather patterns on distant worlds. Some of these planets appear so Earth-like in their characteristics that the absence of detectable biosignatures becomes increasingly difficult to explain through purely statistical arguments. The TRAPPIST-1 system continues to yield surprises as our observations become more detailed. Recent analysis suggests that several of these worlds maintain stable atmospheres and may host subsurface liquid water reservoirs. The system's age, approximately 7.6 billion years, means it has had nearly twice as long as Earth to develop life and potentially intelligence. Yet our most sensitive instruments detect no artificial signals, no atmospheric pollution, no geometric structures that might indicate technological civilization. Each negative result adds statistical weight to the growing body of evidence that technological civilizations might be extraordinarily rare. The mathematics become increasingly stark when you consider that our local galactic neighborhood contains thousands of potentially habitable worlds, many of which have existed for billions of years longer than Earth. The probability that all of these worlds remain lifeless by pure chance approaches levels that challenge our fundamental assumptions about the nature of biological emergence. Recent theoretical work has begun to explore whether the apparent fine-tuning of physical constants might reflect not cosmic coincidence, but observational selection effects that we haven't fully considered. The multiverse hypothesis suggests that our universe represents just one of countless bubble universes, each with different physical laws and constants. We naturally find ourselves in a universe capable of supporting life because we couldn't exist in any other type. But this anthropic reasoning leads to even more profound implications when applied to consciousness and intelligence. If the emergence of self-aware beings requires such precise conditions that it occurs in only a tiny fraction of possible universes, then consciousness might represent an even more extraordinary phenomenon than we realize. Each conscious moment becomes infinitely precious when viewed against the backdrop of countless unconscious realities. The development of artificial intelligence adds urgency to these philosophical considerations. Current machine learning systems are approaching human-level performance in domains that were considered uniquely suited to biological intelligence just decades ago. Language understanding, scientific reasoning, creative expression, and strategic planning all show evidence of artificial capabilities that rival or exceed human performance. Yet these systems remain fundamentally different from human consciousness in ways that we're only beginning to understand. They process information without apparent subjective experience, solve problems without seeming to understand their own reasoning, and generate creative outputs without obvious signs of aesthetic appreciation or emotional engagement. The hard problem of consciousness, explaining how subjective experience arises from information processing, remains as mysterious as ever. Recent neuroscience research has revealed that human consciousness appears to emerge from incredibly complex interactions between multiple brain regions, involving feedback loops and information integration processes that took millions of years to evolve through natural selection. The specific neural architectures required for self-awareness, abstract reasoning, and introspective reflection might be so constraining that they develop only under extraordinary evolutionary circumstances. This biological perspective on consciousness suggests that artificial intelligence might follow completely different developmental pathways that never produce genuine subjective experience. Machine learning systems might become arbitrarily capable at information processing while remaining fundamentally unconscious, creating a form of intelligence that bears no resemblance to the conscious experience that drives human scientific curiosity and philosophical inquiry. The possibility that consciousness represents a uniquely biological phenomenon has profound implications for our understanding of cosmic intelligence. If awareness requires the specific types of neural architectures that emerge through evolutionary processes, then technological civilizations might be limited to biological species that successfully navigate the transition from intelligence to technology. This biological constraint could explain why technological signatures remain so rare despite the apparent abundance of potentially habitable worlds. Recent advances in comparative neuroscience have revealed remarkable similarities in the neural architectures associated with complex cognition across diverse species. The brains of dolphins, elephants, great apes, and humans all show evidence of the large-scale neural networks associated with self-awareness and abstract reasoning. Yet only humans have developed the technological capabilities that make civilizations detectable across interstellar distances. This observation suggests that the transition from biological intelligence to technological capability requires more than just complex neural architectures. Cultural factors, environmental pressures, and perhaps pure historical contingency might play crucial roles in determining whether intelligent species develop detectable technology. The window between achieving sufficient intelligence for technology and developing the social coordination necessary for long-term survival might be vanishingly narrow. Recent studies of human technological development have revealed how dependent our civilization has been on specific environmental conditions and historical circumstances. The availability of easily accessible fossil fuels, the existence of suitable materials for metallurgy, the geographic distribution of resources, and even the timing of climatic changes all influence the pace and direction of technological advancement. An intelligent species evolving under different environmental conditions might face insurmountable barriers to technological development, despite possessing cognitive capabilities equal to or exceeding those of humans. Aquatic environments might prevent the discovery of fire and metallurgy. High radiation environments might limit the development of electronic systems. Extreme gravitational conditions might make space exploration impossible. These environmental constraints could create a vast population of intelligent but non-technological species throughout the galaxy. Such civilizations might develop sophisticated understanding of mathematics, philosophy, and natural science while remaining forever confined to their home planets by circumstances beyond their control. They would possess consciousness and curiosity, but lack the technological signatures that make civilizations detectable through our current search methods. The temporal dimension adds another layer of complexity to the search for extraterrestrial intelligence. Even if technological civilizations are relatively common, they might exist for such brief periods, compared to cosmic timescales, that the probability of detecting them becomes vanishingly small. Human radio-emitting civilization has existed for less than a century out of Earth's 4.5 billion year history. If technological phases typically last only a few centuries before civilizations either destroy themselves or transcend into forms unrecognizable to younger species, then the galaxy might have hosted thousands of technological civilizations throughout its history without any two existing simultaneously. We might be searching for signals from civilizations that vanished millions of years ago or won't emerge for millions of years in the future. Recent modeling of galactic chemical evolution has revealed that the heavy elements necessary for technological civilization only became abundant in our region of the galaxy within the last few billion years. Earlier epochs lacked sufficient quantities of metals like iron, copper, and rare earth elements that appear essential for advanced technology. This suggests that technological civilizations might be a relatively recent phenomenon in cosmic history. So here we are, at the end of our cosmic journey together, having explored one of humanity's most profound questions through the lens of cutting-edge science and sobering mathematics. We've peered into the atmospheres of distant worlds, listened to the radio silence of space, and confronted the possibility that consciousness might be far more precious than we ever imagined. Whether we're alone in this vast cosmic ocean, or simply haven't yet developed the sensitivity to detect our neighbors, the search itself has transformed our understanding of life, intelligence, and our place in the universe. The answer, when it finally comes, will reshape not just astronomy and biology, but the very meaning of what it means to be conscious beings in an evolving cosmos. Until then, the search continues, driven by our fundamental need to understand whether we're truly alone or part of something infinitely larger than ourselves.